Hello and welcome to the Docker for Beginners course. My name is Mumshad Manambat and I will be your instructor for this course. I'm a DevOps and cloud trainer at codecloud.com, which is an interactive hands-on online learning platform. I've been working in the industry as a consultant for over 13 years and have helped hundreds of thousands of students learn technology in a fun and interactive way. In this course, you will learn Docker through a series of lectures that use animation, illustration, and some fun analogies that simplify complex concepts. We have demos that will show you how to install and get started with Docker. And most importantly, we have hands-on labs that you can access right in your browser. I will explain more about it in a bit, but first, let's look at the objectives of this course. In this course, we first try to understand what containers are, what Docker is, and why you might need it, and what it can do for you. We will see how to run a Docker container, how to build your own Docker image. We will see networking in Docker and how to use Docker Compose, what Docker registry is, how to deploy your own private registry, and we then look at some of these concepts in depth and we try to understand how Docker really works under the hoods. We look at Docker for Windows and Mac before finally getting a basic introduction to container orchestration tools like Docker Swarm and Kubernetes. Here's a quick note about hands-on labs. First of all, to complete this course, you don't have to set up your own labs. Well, you may set it up if you wish to have your own environment, and we have a demo as well. But as part of this course, we provide real labs that you can access right in your browser, anywhere, anytime, and as many times as you want. The labs give you instant access to a terminal, to a Docker host, and an accompanying quiz portal. The quiz portal asks a set of questions, such as exploring the environment and gathering information, or you might be asked to perform an action such as run Docker container. The quiz portal then validates your work and gives you feedback instantly. Every lecture in this course is accompanied by such challenging interactive quizzes that makes learning Docker a fun activity. So, I hope you're as thrilled as I am to get started, so let us begin. We're going to start by looking at a high-level overview on why you need Docker and what it can do for you. Let me start by sharing how I got introduced to Docker. In one of my previous projects, I had this requirement to set up an end-to-end application stack, including various different technologies, like a web server using Node.js and a database such as MongoDB, and a messaging system like Redis, and an orchestration tool like Ansible. We had a lot of issues developing this application stack with all these different components. First of all, their compatibility with the underlying OS was an issue. We had to ensure that all these different services were compatible with the version of OS we were planning to use. There have been times when certain versions of these services were not compatible with the OS, and we've had to go back and look at different OS that was compatible with all of these different services. Secondly, we had to check the compatibility between these services and the libraries and dependencies on the OS. We've had issues where one service requires one version of a dependent library, whereas another service requires another version. The architecture of our application changed over time. We've had to upgrade to newer versions of these components, or change the database, etc. And every time something changed, we had to go through the same process of checking compatibility between these various components and the underlying infrastructure. This compatibility matrix issue is usually referred to as the matrix from hell. Next, every time we had a new developer on board, we found it really difficult to set up a new environment. The new developers had to follow a large set of instructions and run hundreds of commands to finally set up their environment. They had to make sure they were using the right operating system, the right versions of each of these components, and each developer had to set all that up by himself each time. We also had different development, test, and production environments. One developer may be comfortable using one OS, and the others may be comfortable using another one. And so we couldn't guarantee that the application that we were building would run the same way in different environments. And so all of this made our life in developing, building, and shipping the application really difficult. So I needed something that could help us with the compatibility issue, and something that will allow us to modify or change these components without affecting the other components, and even modify the underlying operating systems as required. And that search landed me on Docker. With Docker, I was able to run each component in a separate container with its own dependencies and its own libraries, all on the same VM and the OS, but within separate environments or containers. We just had to build the Docker configuration once, and all our developers could now get started with a simple Docker run command. Irrespective of what the underlying operating system they run, all they needed to do was to make sure they had Docker installed on their systems. So what are containers? Containers are completely isolated environments, as in they can have their own processes or services, their own network interfaces, their own mounts, just like virtual machines, except they all share the same OS kernel. We will look at what that means in a bit, but it's also important to note that containers are not new with Docker. Containers have existed for about 10 years now, and some of the different types of containers are LXC, LXD, LXCFS, etc. Docker utilizes LXC containers. Setting up these container environments is hard as they are very low level, and that is where Docker offers a high-level tool with several powerful functionalities, making it really easy for end users like us. To understand how Docker works, let us revisit some basic concepts of operating systems. First, if you look at operating systems like Ubuntu, Fedora, SUSE, or CentOS, they all consist of two things: an OS kernel and a set of software. The OS kernel is responsible for interacting with the underlying hardware, while the OS kernel remains the same, which is Linux in this case. It's the software above it that makes these operating systems different. This software may consist of a different user interface, drivers, compilers, file managers, developer tools, etc. So you have a common Linux kernel shared across all OSs, and some custom software that differentiate operating systems from each other. We said earlier that Docker containers share the underlying kernel. So what does that actually mean, sharing the kernel? Let's say we have a system with an Ubuntu OS with Docker installed on it. Docker can run any flavor of OS on top of it as long as they are all based on the same kernel, in this case, Linux. If the underlying OS is Ubuntu, Docker can run a container based on another distribution like Debian, Fedora, SUSE, or CentOS. Each Docker container only has the additional software that we just talked about in the previous slide that makes these operating systems different, and Docker utilizes the underlying kernel of the Docker host, which works with all OSs above. So what is an OS that do not share the same kernel as this? Windows. And so you won't be able to run a Windows-based container on a Docker host with Linux on it. For that, you will require Docker on a Windows server. Now, it is when I say this that most of my students go, hey, hold on there, that's not true. And they install Docker on Windows, run a container based on Linux, and go, see, it's possible. Well, when you install Docker on Windows and run a Linux container on Windows, you're not really running a Linux container on Windows. Windows runs a Linux container on a Linux virtual machine under the hoods. So it's really Linux container on Linux virtual machine on Windows. We discuss more about this on the Docker on Windows or Mac later during this course. Now you might ask, isn't that a disadvantage then, not being able to run another kernel on the OS? The answer is no, because unlike hypervisors, Docker is not meant to virtualize and run different operating systems and kernels on the same hardware. The main purpose of Docker is to package and containerize applications and to ship them and to run them anywhere, anytime, as many times as you want. So that brings us to the differences between virtual machines and containers, something that we tend to do, especially those from a virtualization background. As you can see on the right, in case of Docker, we have the underlying hardware, infrastructure, and then the OS, and then Docker installed on the OS. Docker then manages the containers that run with libraries and dependencies alone. In case of virtual machines, we have the hypervisor like ESX on the hardware and then the virtual machines on them. As you can see, each virtual machine has its own OS inside it, and then the dependencies, and then the application. The overhead causes higher utilization of underlying resources as there are multiple virtual operating systems and kernels running. The virtual machines also consume higher disk space as each VM is heavy and is usually in gigabytes in size, whereas Docker containers are lightweight and are usually in megabytes in size. This allows Docker containers to boot up faster, usually in a matter of seconds, whereas VMs, as we know, takes minutes to boot up as it needs to boot up the entire operating system. It is also important to note that Docker has less isolation as more resources are shared between the containers, like the kernel, whereas VMs have complete isolation from each other. Since VMs don't rely on the underlying OS or kernel, you can run different types of applications built on different OSs, such as Linux-based or Windows-based apps on the same hypervisor. So those are some differences between the two. Now, having said that, it's not an either container or virtual machine situation. It's containers and virtual machines. Now, when you have large environments with thousands of application containers running on thousands of Docker hosts, you will often see containers provisioned on virtual Docker hosts. That way, we can utilize the advantages of both technologies. We can use the benefits of virtualization to easily provision or decommission Docker hosts as required, at the same time make use of the benefits of Docker to easily provision applications and quickly scale them as required. But remember that in this case, we will not be provisioning that many virtual machines as we used to before, because earlier we provisioned a virtual machine for each application. Now you might provision a virtual machine for hundreds or thousands of containers. So how is it done? There are lots of containerized versions of applications readily available as of today. So most organizations have their products containerized and available in a public Docker repository called Docker Hub or Docker Store. For example, you can find images of most common operating systems, databases, and other services and tools. Once you identify the images you need and you install Docker on your host, bringing up an application is as easy as running a docker run command with the name of the image. In this case, running a docker run Ansible command will run an instance of Ansible on the Docker host. Similarly, run an instance of MongoDB, Redis, and Node.js using the docker run command. If you need to run multiple instances of the web service, simply add as many instances as you need and configure a load balancer of some kind in the front. In case one of the instances were to fail, simply destroy that instance and launch a new one. There are other solutions available for handling such cases that we will look at later during this course. And for now, don't focus too much on the commands. We will get to that in a bit. We've been talking about images and containers. Let's understand the difference between the two. An image is a package or a template, just like a VM template that you might have worked with in the virtualization world. It is used to create one or more containers. Containers are running instances of images that are isolated and have their own environments and set of processes. As we have seen before, a lot of products have been Dockerized already. In case you cannot find what you're looking for, you could create your own image and push it to Docker Hub repository, making it available for public. So if you look at it, traditionally, developers developed applications. Then they hand it over to ops team to deploy and manage it in production environments. They do that by providing a set of instructions, such as information about how the host must be set up, what prerequisites are to be installed on the host, and how the dependencies are to be configured, etc. Since the ops team did not really develop the application on their own, they struggle with setting it up. When they hit an issue, they work with the developers to resolve it. With Docker, the developers and operations teams work hand in hand to transform the guide into a Docker file with both of their requirements. This Docker file is then used to create an image for their applications. This image can now run on any host with Docker installed on it and is guaranteed to run the same way everywhere. So the ops team can now simply use the image to deploy the application. Since the image was already working when the developer built it and operations have not modified it, it continues to work the same way when deployed in production. And that's one example of how a tool like Docker contributes to the DevOps culture. Well, that's it for now, and in the upcoming lecture, we will look at how to get started with Docker. We will now see how to get started with Docker. Now, Docker has two editions, the Community Edition and the Enterprise Edition. The Community Edition is the set of free Docker products. The Enterprise Edition is the certified and supported container platform that comes with enterprise add-ons like the image management, image security, universal control plane for managing and orchestrating container runtimes. But of course, these come with a price. We will discuss more about container orchestration later in this course, and along with some alternatives. For now, we will go ahead with the Community Edition. The Community Edition is available on Linux, Mac, Windows, or on cloud platforms like AWS or Azure. In the upcoming demo, we will take a look at how to install and get started with Docker on a Linux system. Now, if you are on Mac or Windows, you have two options. Either install a Linux VM using VirtualBox or some kind of virtualization platform, and then follow along with the upcoming demo, which is really the most easiest way to get started with Docker. The second option is to install Docker Desktop for Mac or Docker Desktop for Windows, which are native applications. So if that is really what you want, check out the Docker for Mac and the Windows sections towards the end of this course, and then head back here once you're all set up. We will now head over to a demo, and we will take a look at how to install Docker on a Linux machine. In this demo, we'll look at how to install and get started with Docker. First of all, identify a system, physical or virtual machine, or laptop that has a supported operating system. In my case, I have an Ubuntu VM. Go to docs.docker.com and click on Get Docker. You will be taken to the Docker Engine Community Edition page. That is the free version that we are after. From the left-hand menu, select your system type. I choose Linux in my case, and then select your OS flavor. I choose Ubuntu. Read through the prerequisites and requirements. Your Ubuntu system must be 64-bit and one of the supported versions like Disco, Cosmic, Bionic, or Xennial. In my case, I have a Bionic version. To confirm, view the etc release file. Next, uninstall any older version if one exists. So let's just make sure that there's none on my host. So I'll just copy and paste that command. And I confirm that there are no older version that exists on my system. The next step is to set up repository and install the software. Now, there are two ways to go about this. The first is using the package manager by first updating the repository using the apt-get update command, then installing the prerequisite packages, and then adding Docker's official GPG keys, and then installing Docker. But I'm not going to go that route. There is an easier way. If you scroll all the way to the bottom, you will find the instructions to install Docker using the convenience script. It's a script that automates the entire installation process and works on most operating systems. Run the first command to download a copy of the script, and then run the second command to execute the script to install Docker automatically. Give it a few minutes to complete the installation. The installation is now successful. Let us now check the version of Docker using the docker version command. We've installed version 19.03.1. We will now run a simple container to ensure everything is working as expected. For this, head over to Docker Hub at hub.docker.com. Here you will find a list of the most popular Docker images like Nginx, MongoDB, Alpine, Node.js, Redis, etc. Let's search for a fun image called whalesay. Whalesay is Docker's version of cowsay, which is basically a simple application that prints a cow saying something. In this case, it happens to be a whale. Copy the docker run command given here. Remember to add sudo, and we will change the message to hello world. On running this command, Docker pulls the image of the whalesay application from Docker Hub and runs it. And we have our whale saying hello. Great. We're all set. Remember, for the purpose of this course, you don't really need to set up a Docker system on your own. We provide hands-on labs that you will get access to, but if you wish to experiment on your own and follow along, feel free to do so. We now look at some of the Docker commands. At the end of this lecture, you will go through a hands-on quiz where you will practice working with these commands. Let's start by looking at Docker run command. The Docker run command is used to run a container from an image. Running the Docker run nginx command will run an instance of the nginx application on the Docker host if it already exists. If the image is not present on the host, it will go out to Docker Hub and pull the image down. But this is only done the first time. For the subsequent executions, the same image will be reused. The Docker ps command lists all running containers and some basic information about them, such as the container ID, the name of the image we use to run the containers, the current status, and the name of the container. Each container automatically gets a random ID and name created for it by Docker, which in this case is silly Samet. To see all containers running or not, use the -a option. This outputs all running as well as previously stopped or exited containers. We'll talk about the command and port fields shown in this output later in this course. For now, let's just focus on the basic commands. To stop a running container, use the docker stop command, but you must provide either the container ID or the container name in the stop command. If you're not sure of the name, run the docker ps command to get it. On success, you will see the name printed out, and running docker ps again will show no running containers. Running docker ps-a, however, shows the container silly Samet and that it is in an exited state a few seconds ago. Now, what if we don't want this container lying around consuming space? What if we want to get rid of it for good? Use the docker rm command to remove a stopped or exited container permanently. If it prints the name back, we're good. Run the docker ps command again to verify that it's no longer present. Good, but what about the nginx image that was downloaded at first? We're not using that anymore. So how do we get rid of that image? But first, how do we see a list of images present on our host? Run the docker images command to see a list of available images and their sizes. On our host, we have 4 images: nginx, redis, ubuntu, and alpine. We will talk about tags later in this course when we discuss about images. To remove an image that you no longer plan to use, run the docker rmi command. Remember, you must ensure that no containers are running off of that image before attempting to remove the image. You must stop and delete all dependent containers to be able to delete an image. When we ran the docker run command earlier, it downloaded the Ubuntu image as it couldn't find one locally. What if we simply want to download the image and keep so when we run the docker run command, we don't want to wait for it to download? Use the docker pull command to only pull the image and not run the container. So in this case, the docker pull ubuntu command pulls the Ubuntu image and stores it on our host. Let's look at another example. Say you were to run a Docker container from an Ubuntu image. When you run the docker run ubuntu command, it runs an instance of Ubuntu image and exits immediately. If you were to list the running containers, you wouldn't see the container running. If you list all containers, including those that are stopped, you will see that the new container you ran is in an exited state. Now, why is that? Unlike virtual machines, containers are not meant to host an operating system. Containers are meant to run a specific task or process, such as to host an instance of a web server or application server or a database, or simply to carry some kind of computation or analysis task. Once the task is complete, the container exits. A container only lives as long as the process inside it is alive. If the web service inside the container is stopped or crashed, then the container exits. This is why when you run a container from an Ubuntu image, it stops immediately. Because Ubuntu is just an image of an operating system that is used as the base image for other applications. There is no process or application running in it by default. If the image isn't running any service, as is the case with Ubuntu, you could instruct Docker to run a process with the docker run command. For example, a sleep command with a duration of 5 seconds. When the container starts, it runs the sleep command and goes into sleep for 5 seconds, post which the sleep command exits and the container stops. What we just saw was executing a command when we run the container. But what if we would like to execute a command on a running container? For example, when I run the docker ps command, I can see that there is a running container which uses the Ubuntu image and sleeps for 100 seconds. Let's say I would like to see the contents of a file inside this particular container. I could use the docker exec command to execute a command on my Docker container. In this case, to print the contents of the etc hosts file. Finally, let's look at one more option before we head over to the practice exercises. I'm now going to run a Docker image I developed for a simple web application. The repository name is codecloud/simple-web-app. It runs a simple web server that listens on port 8080. When you run a docker run command like this, it runs in the foreground or in an attached mode, meaning you will be attached to the console or the standard out of the Docker container, and you will see the output of the web service on your screen. You won't be able to do anything else on this console other than view the output until this Docker container stops. It won't respond to your inputs. Press the Ctrl+C combination to stop the container, and the application hosted on the container exits, and you get back to your prompt. Another option is to run the Docker container in the detached mode by providing the -D option. This will run the Docker container in the background mode, and you will be back to your prompt immediately. The container will continue to run in the backend. Run the docker ps command to view the running container. Now, if you would like to attach back to the running container later, run the docker attach command and specify the name or ID of the Docker container. Now remember, if you're specifying the ID of a container in any Docker command, you can simply provide the first few characters alone, just so it is different from the other container IDs on the host. In this case, I specify A043D. Now, don't worry about accessing the UI of the web server for now. We will look more into that in the upcoming lectures. For now, let's just understand the basic commands. We'll now get our hands dirty with the Docker CLI, so let's take a look at how to access the practice lab environments next. Hello and welcome to this demo. In this demo, we're going to look at some of the basic Docker commands, some basic commands that are necessary for one to get started and in order to play around with Docker. So in the previous demo, we installed Docker following a set of instructions from the Docker documentation site, and we ran a sample Docker Hello World container and a Docker Ubuntu image. In this demo, we're going to look at some other commands. So just to start with, we will run the Docker. We'll start with the docker run command. So the docker run command is used to run a container from an image. So you need to specify an image name. To find out what images you can use, go to the Docker Hub website and go to explore, and you should be able to see a lot of default official images available, like the hello world that we just saw. Let's say you would like to try a CentOS. You could just do, if you click on this, you'll see the instructions on running the CentOS. So you could simply do, as you can see here, it just says docker pull CentOS. So you could simply do a docker run CentOS, and that should first try and find if there's a CentOS image available locally. If not, it's just going to go out and download the latest image or the latest version of the CentOS image. As you can see here, the name, if you simply specify a name like this as CentOS, it's going to look at the library repository. Library is a default Docker repository which has the official images. So if you go to the go back to the Docker Hub website, all the official images, such as those that are available here, can simply be downloaded with just the name of that particular image. On the other hand, if you develop your own images, for example, if I go to my dashboard and I have some images that I use here, such as the Ansible playable, etc. If I need to run any of these, then I need to use the name in this particular format, called as the first with the user ID. So mmshad is my user ID, and and then followed by a / and the name of the repository. So these you should use names in this format if you are using your own images, or you could simply use the name directly, but then these need to be official repositories that are supported by Docker. So I have this new image downloaded called Docker CentOS. Now it's not actually going to, as you can see, I'm back to my prompt. It ran, but it exited immediately, and that's because we didn't ask it to do anything. So it's just the CentOS image is just a base image for the CentOS operating system. As you know, Docker is used to run services and applications. So if you want to keep that container alive, you need to be running something. So I'm just going to run it again. And this time it won't take long because the image is already pulled. And I'm going to ask it to run the bash command. And if I want to automatically be logged into the Docker container when it's run, I should be using the -it options. We'll look at what these options are in a bit. So now, as you can see, the prompt has changed. So what's happened is Docker ran the CentOS container, which is the CentOS operating system, and then ran the bash command. And then it logged me in directly to the container since I specified the -it options. So I'm now inside the Docker container. If you look at this, the prompt, it says root at a unique ID. This is the unique ID for the Docker container, whereas earlier I was at the Docker prompt. Okay, so I'm going to, just to check the operating system that I'm on, I'm going to do a cat /etc/* release *. And as you can see, I am on the CentOS Linux OS. So I'm inside the CentOS. Okay, so I'm going to exit now, and I'm just going to clear my screen. So that's the first command. So docker run, and an image name will run a Docker container. The next command that we're going to see is the ps command. So I'm going to run the docker ps command. The docker ps command lists all the running containers. In this case, I do not have a running container because I just ran the CentOS. I logged into that CentOS. I ran a couple of commands and then I exited, and that actually took me out of the container, and the container wasn't running any service. So Docker exited that container. The docker ps command lists all the running containers only. Now I do not have any running containers. So what I'm going to do is I'm going to run the CentOS container once again. So I'm going to say docker run CentOS, And earlier I gave the bash command. Now I'm just going to run the sleep command. I'm just going to sleep for 20 seconds. So the container is going to come up. It's just going to sleep for 20 seconds, and then it's just going to shut down. And then I want to run this in the background. So I'm just going to give a -D so that I get back to my terminal. And as you can see, this is the container ID, and it just ran the container. Now if I run the docker ps command, I will see that this is the container ID. This is the image it's running off of. The command that is running is sleep 20, so it's going to sleep for 20 seconds. It was created 7 seconds ago. It's been up for 6 seconds, and it's got a funny name called flamboyant noise. Okay, now we asked it to just sleep for 20 seconds, just to keep it alive for 20 seconds. So if I run the docker ps command now, probably it should have gone. Yes, so it's gone because it slept for 20 seconds, and then that was the end of that command. And so since the command exited, the Docker container exited as well, because it didn't have anything to run or any service running on it. Okay, so that's a quick example of docker ps command. Now, if you'd like to see all the containers you ran in the past, and all the exited containers especially, so you could do run a docker ps -a docker ps command with the -a option, and you'll see all the containers that exited. So the last one that we ran was the CentOS with the sleep command, and it was created about a minute ago, and it exited about 54 seconds ago. Similarly, before that, we ran the CentOS with the bash the first time, and I was on it for about 3 minutes checking the OS, etc. And it was created about 4 minutes ago. Similarly, you can see all the previous containers that we ran. So when you run a container and it exits, the container actually lives on the disk drive. Now that we have seen how to list all the running containers, let's look at another example. So I'm going to run the same command to run a CentOS, but in this case, I'm going to sleep for around 2000 seconds. And what this will mean is that it'll run a CentOS container, and then it'll sleep for 2000 seconds. And after that, it's going to exit. Now, if I run the docker ps command now, I should be able to see that. So it's up for 13 seconds, and it's just going to be alive for 2000 seconds. Now, for some reason, if I want to stop or kill this container right now, I could use the docker stop command. So I do a docker stop, and then say serine pasture. I could either provide the name of the container, or I could give the container ID. And when I do that, it takes a couple of seconds to stop or force kill that particular Docker container. Okay, now if I do a docker ps, I can see that it's no longer there. If I do a docker ps-a, I will be able to see that the container that I just ran at the top, it was created about a minute ago, and it exited about 9 seconds ago. And you can see the exit code in here. So the exit code for the previous containers are all 0 because they exited under normal conditions. But since I killed it using the stop command, you can see the exit code, which is 137 right here. Okay, so now I have a lot of containers that I ran previously, and I kind of want to clean it up. So what can I do to remove these containers? For that, I could use the docker rm command. So I do a docker rm. I'm going to start with the first one. I'm going to provide this container ID. So I could either refer to the containers with the container ID or with the name right here. So in this case, I'm going to select this one. I'm going to provide the name. So I've removed 2 containers, and if I do a docker ps-a, I will be able to see that those are gone. So that's what you should do to reclaim disk space. Similarly, I'm going to get rid of all of this. Now I don't need to provide the entire container ID. I could actually provide just the first few letters. So I say 345, and then I can provide multiple container IDs or names in the same command as well. So this one is 345, the next one is E0A, the next one is 773. So it's going to remove all of them at once. Now if I run the docker ps command, I can see that all those three are gone. So this is a way to remove the Docker containers. So I'm just going to clean up all that. 6.2 and 5b. So I don't have any containers running or dead at the moment. So that's good. So I've cleaned up all of that. Now the image that I pulled, which is I've actually pulled 3 images so far. First the hello world, then the Ubuntu, and then the CentOS. Now to see the images that I currently have, I could run the docker images command. Then I can actually see the images. I actually pulled another one called BusyBox, which is a really lightweight toolkit, as you can call it. It's just around 1.13 MB in size. So if you want to really test something really small, you could actually use this particular image. So now what do I do to get rid of these images? Let's say I pulled these just to test them and I want to get rid of them. I could do a docker rm command followed by the name docker rmi command. So rm is used for removing containers, rmi is used for removing images. So I do a docker rmi and then say busybox. That removes the busybox. And then I do docker rmi and remove the Ubuntu. That removes the Ubuntu. So now I have 2 left. And just to demo something real quick, I'm going to run a container based off of CentOS. And if I do a docker ps-a now, I can see that there's a container based on the CentOS image. Now, the reason I did this is if I try to delete, now I can see that if I try to delete the docker image for CentOS using the rmi command, it'll actually fail, telling me that this particular image is being used by a particular container. So we actually have a container dependent on this particular image that you can see here. So we need to get rid of all the containers first before removing the image. So we're going to do a docker rm and 8e to remove the container, and we make sure the container no longer exists, and then we remove the image using docker rmi CentOS, and now the image is gone. Similarly, we're going to remove the hello world image. Okay, so we do not have any containers and we do not have any images running at the moment. Okay, so that's some of the basic Docker commands. Let me also show you another command, which is pull. So if you do the docker pull, earlier when we ran the docker run command with Ubuntu, it first looks for an image locally. If not, it's going to go out and pull the image. And then it's going to pull the image and immediately run that image, run a container with that image. Now, if we don't want Docker to run immediately, and if we just want to pull an image and just to keep it so that later on, if we were planning to run it, we don't want to spend time pulling the image, you could simply pull the image alone using the docker pull command. So you do a docker pull and say Ubuntu, and that goes out and pulls the Docker image and stores it locally on the local system. Okay, so it's pulled the image. Now, if I now run the docker images command, I can see the Ubuntu image is there. Okay, so there's one more thing to look at before we end this demo, and that's running a command on a particular container. Okay, so we're going to run a Ubuntu container. So we're going to do a Docker run Ubuntu, and we're going to keep it alive for, let's say, 100 seconds. And we want it to run in the background so we get back to our prompt or console. So we're going to do run it in the background using the -d. And so there it goes. If you do a docker ps command, you can see that it's running and it's sleeping for 100 seconds. Now, while a Docker container is running like this, if you'd like to run a particular command on the currently executing container, for example, if you'd like to see the contents of a particular file which is inside the container, you might want to run a cat command on a particular file. So to run a command inside a running container, first identify the container you want to work with, and then do a docker run, docker exec, and provide the container ID. In this case, this is the container ID, and then followed by the command that you wish to run. So I'm just going to run the cat /etc/star release file. So I'm just going to look at the release file to understand what version of the OS is running. So the exec command basically runs or executes a command on a running container. When I hit this, it actually runs this particular command inside the container and gives me an output. So that's basically it for this demo. We just looked at some of the basic commands, and some of the additional parameters we looked at. We're going to look at them a little bit more in detail in the upcoming demos and lectures. So this is it for now. So these are some basic commands. So go ahead and play around with it. Thank you for your time, and see you in the next lecture. Let me now walk you through the hands-on lab practice environment. The labs open up right in your browser. I would recommend to use Google Chrome while working with the labs. The interface consists of two parts, a terminal on the left and a quiz portal on the right. The quiz portal on the right gives you challenges to solve. Follow the quiz and try and answer the questions asked and complete the tasks given to you. Each scenario consists of anywhere from 10 to 20 questions that need to be answered within 30 minutes to an hour. At the top, you have the question numbers. Below that is the remaining time for your lab. Below that is the question. If you are not able to solve the challenge, look for hints in the hints section. You may skip a question by hitting the skip button in the top right corner. But remember that you will not be able to go back to a previous question once you have skipped. If the quiz portal gets stuck for some reason, click on the quiz portal tab at the top to open the quiz portal in a separate window. The terminal gives you access to a real system running Docker. You can run any Docker command here and run your own containers or applications. You would typically be running commands to solve the task assigned in the quiz portal. You may play around and experiment with this environment, but make sure you do that after you've gone through the quiz, so that your work does not interfere with the tasks provided by the quiz. So let me walk you through a few questions. There are two types of questions. Each lab scenario starts with a set of exploratory multiple choice questions where you're asked to explore and find information in the given environment and select the right answer. This is to get you familiarized with the setup. You're then asked to perform tasks like run a container, stop them, delete them, build your own image, etc. Here, the first question asks us to find the version of Docker server engine running on the host. Run the Docker version command in the terminal and identify the right version. Then select the appropriate option from the given choices. Another example is the fourth question, where it asks you to run a container using the Redis image. If you're not sure of the command, click on Hints and it will show you a hint. We now run a Redis container using the docker run Redis command. Wait for the container to run. Once done, click on Check to check your work. You have now successfully completed the task. Similarly, follow along and complete all tasks. Once the lab exercise is completed, remember to leave a feedback and let us know how it went. A few things to note. So if you catch yourself logged out during a peak hour, please wait for some time and try again. Also, remember to not store any private or confidential data on these systems. Remember that this environment is for learning purposes only and is only alive for an hour, after which the lab is destroyed. So does all your work. But you may start over and access these labs as many times as you want until you feel confident. That's it for now. Head over to the first challenge, and I will see you on the other side. We will now look at some of the other Docker run commands. At the end of this lecture, you will go through a hands-on quiz where you will practice working with these commands. We learned that we could use the docker run redis command to run a container running a Redis service. In this case, the latest version of Redis, which happens to be 5.0.5 as of today. But what if we want to run another version of Redis, like for example an older version, say 4.0? Then you specify the version separated by a colon. This is called a tag. In that case, Docker pulls an image of the 4.0 version of Redis and runs that. Also, notice that if you don't specify any tag as in the first command, Docker will consider the default tag to be latest. Latest is a tag associated to the latest version of that software, which is governed by the authors of that software. So as a user, how do you find information about these versions and what is the latest? At dockerhub.com, look up an image and you will find all the supported tags in its description. Each version of the software can have multiple short and long tags associated with it, as seen here. In this case, the version 5.0.5 also has the latest tag on it. Let's now look at inputs. I have a simple prompt application that, when run, asks for my name, and on entering my name, prints a welcome message. If I were to Dockerize this application and run it as a Docker container like this, it wouldn't wait for the prompt. It just prints whatever the application is supposed to print on standard out. That is because, by default, the Docker container does not listen to a standard input. Even though you're attached to its console, it is not able to read any input from you. It doesn't have a terminal to read inputs from. It runs in a non-interactive mode. If you'd like to provide your input, you must map the standard input of your host to the Docker container using the -i parameter. The -i parameter is for interactive mode, and when I input my name, it prints the expected output. But there is something still missing from this: the prompt. When we ran the app, at first, it asked us for our name. But when Dockerized, that prompt is missing, even though it seems to have accepted my input. That is because the application prompts on the terminal, and we have not attached to the container's terminal. For this, use the -t option as well. The -t stands for a pseudo terminal. So with the combination of -i and t, we're now attached to the terminal as well as in an interactive mode on the container. We will now look at port mapping or port publishing on containers. Let's go back to the example where we run a simple web application in a Docker container on my Docker host. Remember, the underlying host where Docker is installed is called Docker host or Docker engine. When we run a containerized web application, it runs and we are able to see that the server is running. But how does a user access my application? As you can see, my application is listening on port 5000. So I could access my application by using port 5000. But what IP do I use to access it from a web browser? There are two options available. One is to use the IP of the Docker container. Every Docker container gets an IP assigned by default. In this case, it is 172.17.0.2. But remember that this is an internal IP and is only accessible within the Docker host. So if you open a browser from within the Docker host, you can go to http://172.17.0.1:5000 to access the IP address. But since this is an internal IP, users outside of the Docker host cannot access it using this IP. For this, we could use the IP of the Docker host, which is 192.168.1.5. But for that to work, you must have mapped the port inside the Docker container to a free port on the Docker host. For example, if I want the users to access my application through port 80 on my Docker host, I could map port 80 of localhost to port 5000 on the Docker container using the -p parameter in my run command like this. And so the user can access my application by going to the URL http://192.168.1.5:80. And all traffic on port 80 on my Docker host will get routed to port 5000 inside the Docker container. This way, you can run multiple instances of your application and map them to different ports on the Docker host, or run instances of different applications on different ports. For example, in this case, I am running an instance of MySQL that runs a database on my host and listens on the default MySQL port, which happens to be 3306, or another instance of MySQL on another port, 8306. So you can run as many applications like this and map them to as many ports as you want. And of course, you cannot map to the same port on the Docker host more than once. We will discuss more about port mapping and networking of containers in the network lecture later on. Let's now look at how data is persisted in a Docker container. For example, let's say you were to run a MySQL container. When databases and tables are created, the data files are stored in location /var lib mysql inside the Docker container. Remember, the Docker container has its own isolated file system, and any changes to any files happen within the container. Let's assume you dump a lot of data into the database. What happens if you were to delete the MySQL container and remove it? As soon as you do that, the container along with all the data inside it gets blown away, meaning all your data is gone. If you would like to persist data, you would want to map a directory outside the container on the Docker host to a directory inside the container. In this case, I create a directory called /opt/data dir and map that to var lib mysql inside the Docker container using the -v option and specifying the directory on the Docker host followed by a colon and the directory inside the Docker container. This way, when Docker container runs, it will implicitly mount the external directory to a folder inside the Docker container. This way, all your data will now be stored in the external volume at /opt/data directory, and thus will remain even if you delete the Docker container. The docker ps command is good enough to get basic details about containers like their names and IDs. But if you'd like to see additional details about a specific container, use the docker inspect command and provide the container name or ID. It returns all details of a container in a JSON format, such as the state, mounts, configuration data, network settings, etc. Remember to use it when you're required to find details on a container. And finally, how do we see the logs of a container we ran in the background? For example, I ran my simple web application using the -d parameter, and it ran the container in a detached mode. How do I view the logs, which happens to be the contents written to the standard out of that container? Use the docker logs command and specify the container ID or name like this. Well, that's it for this lecture. Head over to the challenges and practice working with Docker commands. Hello and welcome to this demo. In this demo, we're going to look at some of the advanced options with Docker commands, some of the advanced options available with running Docker containers using the Docker run command. So in the previous demos, we saw how to install Docker and how to set it up and how to run some images, and we saw some of the basic commands, such as the commands to run a Docker container, to look at the list of running and dead Docker containers, to execute a command inside a Docker container, etc. In this case, in this demo, we're going to look a little bit more about running Docker containers, but some advanced options available for us. So I'm just going to run the docker ps command to check if there are any existing running containers, and I see there are no containers running. And earlier we saw that we could run an Ubuntu or a container based off of an Ubuntu or a CentOS by running the docker run Ubuntu command. So I'm just going to run docker run Ubuntu, and I'm going to append a command next to this docker run, just so it runs the when it runs or starts up the Ubuntu container, and before it exits, it can run this particular command and give me the output. So what I want to do is I want to see the version of Ubuntu running. So we downloaded, or Docker downloaded an image of Ubuntu automatically, but I don't know what version of Ubuntu it is running. So I'm just going to run this, append this particular command to the end of the run command. So cat etc / release *, and so it ran the Docker container, ran this particular command, and gave me this output. And as you can see, the version is 16.04. But what if I want to run another version of this particular operating system? So the first thing that I need to do is go to the Docker Hub site, identify the repository I'm using, and if you look inside this particular repository, in this case Ubuntu, you will see a list of supported tags. So that's the first thing in the description. So supported tags and respective Docker files. So these are the tags that it supports. For example, 16.04 is actually the default and the latest. As we know, if you don't specify any tag, it's going to assume that it's going to assume a latest tag. So since we didn't specify any tag when we ran the docker Ubuntu command right here, it actually assumed to be the latest tag, which is why it downloaded the 16.04 image. Now what if I want to run another version, let's say 17.10? If I want to run this particular version, what I could do is just append this tag to the Ubuntu, the name of the image. So I'm going to run the same command as before, which is docker run Ubuntu. I'm also going to print out the version of the OS using the cat command, and right here I could append a tag. So the tag is to be appended following a colon, and if you look at this list here, it could either be 17.10, it could be artful dash and then this particular number here, or it could be artful, or it could be devel. It could be any of this. So these are all supported tags for the same version, which is 17.10. So I'm going to just give 17.10 for now. And it's first going to find out if that image is available locally. It's definitely not. So it's going to go out to Docker Hub and find out the image. So it's going to download the image from Docker Hub. And okay, so it's downloaded the image and run it, and when it ran the cat command to print out the version of Ubuntu, and as you can see, the version of Ubuntu is 17.10. So it's downloaded the right version because we provided a different tag. So that's about tags. This way you can tag your images differently for different purposes. You can use tags for versioning, etc. The next thing that we're going to do is we're going to see attach and detach modes. As we did before, I'm going to run a Docker container with Ubuntu, and what I'm going to do is I'm just going to keep it alive by using the sleep command. So I'm just going to run the sleep command and keep it alive for, let's say, 100 seconds. Now, okay, I'm just going to change that to 15. Okay, now when I run this, what I expect is for Docker to run a container based off of Ubuntu and run this particular application. In my case, the application is just a sleep command. So it's going to run the sleep command for 15 seconds and it's going to exit the container. Now, if I hit enter, I can actually see that I'm kind of stuck in the console. I don't see anything. If I do a Control C, it doesn't actually take me out. I'm kind of stuck, and I cannot come out of this particular console until the OS or the container automatically exits, which it's done now. So it waited for 15 seconds and it kind of exited. Now, if I were to run an actual application instead of the test sleep command that I ran here, such as running a web server, which is supposed to stay alive permanently, then I wouldn't be able to come out of this, and the console would just show me the output of that application I'm running. Now, this is the default way how a container runs. It doesn't really matter. You could always use another session or terminal to your Docker host. For example, I'm going to run the same command, but in this case, I'm going to add 2 zeros to keep it alive for 1,500 seconds. Now, in this case, as you can see, if I hit Control C, whatever I try to do, it doesn't actually come out of that. It's because the Docker container is running in the foreground. And what I could always do is I could establish another duplicate connection to my Docker host. And once I'm logged in, I run the Docker ps command to see the running images, and then I can actually stop that if I want to by using the Docker stop and specifying the container ID. So this stops my container, and if I go back, it takes a couple of seconds to stop, and as soon as it stops the container, I should be back to my console right here. So as you can see, when I stopped the container from here, I'm actually back to my prompt right here. It isn't actually anything of a serious concern, but the next time you run the Docker container, if you'd like to run it in the background or in a detached mode, you could actually specify the -d parameter. So the -d parameter is used to run it in the detached mode in the background when it starts. So as you can see, it's listed, this is the actual container ID, the unique container ID. And so this means that it's actually successful in running. Now, if you run the Docker ps command here, you can actually see the information about the container. So if you look at this right now, this is the container ID, unique container ID. It's actually this big, but when you see it here, it just takes the first few characters and it displays that here. So it's running the Docker in the detached mode now, and I'd like to attach back to it. So I'm going to do for that you could actually do a Docker attach and then specify the container ID, and this will get you back to the Docker. This will bring Docker process container and run it in the foreground. Now I'm back to the same situation again because it's currently I'm actually attached to the Docker container and nothing actually works. So I'm going to go back to the other host and I'm going to I'm going to go back to the other terminal on the same host, and I'm going to stop the Docker container. Okay, so I'm back to my prompt here. Okay, so I'd like to show the same example with another Docker image. For example, I have another Docker image called timer, which simply prints the time, the current time, onto the screen every second. So I'm going to run that image, and as you can see, it prints the time on the screen every second. Now this runs infinitely, so this Docker container never stops. It just keeps printing the time onto the screen infinitely. Now Since I'm running it without any additional parameters, it runs in the foreground or in the attached mode. If you'd like to run it in the background, run it with the -d parameter. And if you go back, run the docker ps command, you'll see that it's running, but you cannot actually see the output. So if you run the docker attach command and provide the container ID, and you're back to the console of the Docker container, and you can see the output being displayed. Okay, so let's explore some additional Docker images from Docker Hub. So something that I'm interested in is Jenkins. So Jenkins is, as you might know already, is a build system. So let's say if you wanted to try a new application like this, in fact, this is my favorite way of trying out any application. So Jenkins is a continuous integration and delivery server. And if I haven't worked with it before, and if I just want to play around with it, get some hands-on experience on it, instead of going through the installation instructions and installing a lot of dependencies on my underlying host, what I would like to do is simply run Jenkins as a container and just play around with it that way. So if you look at the site here, you can see instructions on running Jenkins. So the repository name is just Jenkins, and that should get you started. So the ideal way, what we have seen until now is simply running containers like this, called Jenkins, and it should go out, pull the Jenkins images and layers, and run an instance of Jenkins. Now, as you know, Jenkins is a web server. So what we're expecting is once we deploy this particular container, we're actually expecting to go to a website, to a browser, and browse to this Jenkins server and access the web UI. So let me just go back. We'll wait for it to pull down the image. Okay, so it's just finished pulling the image, and as you can see, it's extracted, and Jenkins is actually running. So it started Jenkins and is actually running. Okay, so all I did was run a docker run Jenkins command, and it just pulled down the Jenkins latest version of Jenkins and ran it. Now, how do I access it? So if I go to the my the UI of my host, so this is my Docker host, and I actually this is the same host where I have a terminal here, and this is just the UI of that host. Now what I'm going to do is, if I run the docker ps command here, I'll be able to see that it's Jenkins is running, and it's on port 8080 and 50,000. Now, as we discussed in the lecture, there are two ways to access the web, this particular application on the web UI. One is using the internal IP, and two is using by mapping a port to my Docker host and accessing it using the external IP. Now, to access it using the internal IP, you need to be inside your Docker host, which is where I am. This is the user interface for my Debian Docker host. So if I open up a browser and go to the IP address, so what IP address should I be using here? So it should be the internal IP. To find out the internal IP of the Docker container, go back here. So if I run the docker ps command, I see the container, and to find out the internal IP of my Jenkins container, I could use the docker inspect command. So to run the docker inspect command followed by the container ID. And when I do that, I actually see a lot of information about my Docker container, the status, the image that it's using, and all of that. And if you scroll down in the network section, under networks, you'll see that it's using the bridge network. We'll talk about networks in a bit. But right here, if you look at the IP address, you can see the IP address here. So it's 172.17.0.2. So this is the IP that I would use if I were to access this Docker container from inside my host. So I'm going to go back to the UI for my host, and I have a Firefox running. Enter the IP 172.17.0.2 followed by port 8080. And I'm actually at on the Jenkins page. So and then I follow the instructions that I have here. So if you look at the output after you run the docker run command, you will be able to see that there's an admin user has been created and a password generated automatically. So I'd be using this password to unlock and start configurations on the Jenkins. But as you can see, we are on the web page by using the internal IP, so that's good. Now, how do I access it externally? So if I open a web page, and go to the IP of my Docker host, which is 192.168.1.14, and if I try to access the Jenkins server using that IP address, I won't be able to access. This is because that particular port or service is not listening on the Docker host. Now, in order to do that, as we saw in the lecture, you need to add a port mapping. So you cannot add a port mapping while the service is running, so you have to stop. So I'm going to try and stop the Docker container. And if you do a docker ps, I see that it's no longer running. And I'm going to use the same docker run command. And in this case, I'm going to map the port 8080 to the port on the Docker host. And I'm going to run it again. And if I go back to my browser and refresh, I should now be able to see the Jenkins page. Okay, cool. So I can just follow the instructions right here and get started with it. So that's really cool. So I didn't have to install dependencies or follow a lot of set of instructions or install binaries, etc. To get started with Jenkins or any application like that. It's as easy as running the Docker container for that particular application. So we've done port mapping, and if you look at this instructions right here, it also gives you instructions on mapping a volume. This is because, as you can read here, Jenkins will store the data in your home directory on the host. So by default, Jenkins stores the data in var Jenkins home inside of the Jenkins container. And if you want to save that information, you need to map a volume. So just to demo that here, I've actually provided the password, and I've set the initial password, and I'm just going to install it and set it up real quick. So I'm going to install suggested plugins, and it's going to take a few minutes for it to install some of the default plugins. So I'm just going to give it some time. So all that I'm trying to do here is I'm just trying to make some configuration changes on my Jenkins. Setting it up is a configurational change. Setting a password, etc., or installing plugins are all configurational changes. So I want to see if the changes that I make will live if I were to stop the container and restart it, or remove the Jenkins container and run another instance of Jenkins, and will I be able to still see the differences that I made? Okay, so it's installed all the default plugins, and I'm going to create a first user. So I'm going to create an admin user, provide a password, provide a full name and an email address. And we'll save and finish. Okay, so I'm all set. Jenkins is ready, and I'm going to start a job. I'll add something like enter an item name, for example, test job or something. And I'm going to select a freestyle project and click OK. Okay, so if I go back to my homepage on Jenkins, I see that there's a test job created. So I have made some configurational change. Now, if I go back and stop my container, and if I do a docker ps, I don't see any container running. And if I refresh this page, I see that it's gone. Okay, now if I were to rerun another container using the same command, and so it comes back saying Jenkins initial setup is required, and Jenkins is fully up and running. So if I go back to the browser and refresh the page, now this is since I ran the docker run command, so it's a new container that's running, and obviously we're back to square one where we're asked to set up an initial administrator password, and we'll have to do everything that we just did all over again. Now, in order to persist that data across Docker containers or across Docker container restarts, or even if you destroy Docker containers and run a new container, and if you'd like to persist your configuration data, as you can see here in the instructions, you've got to map a volume. And this is the same for MySQL database or anything like that. So what I'm going to do is I'm going to create a local directory called my Jenkins data. And what I'm going to do is when I run the Docker container next time, I'm going to map that volume, which is root my Jenkins data, to the location where where Jenkins Docker container stores its data by default. That's under Jenkins home. So I'm going to put that, and I'm going to run. So there's a permission issue. There's you have that instruction here. So we could use -u and specify another user. So I'm going to start it with the root user. Okay, so since this is the first time we're mapping a directory, we're just going to go back and we'll have to do everything once. So I'm going to copy this password. I'm just going to quickly redo what we just did before. And I'm going to create a new job. Okay, so I've set up Jenkins and I've created a test job. Now I'm going to go back and stop this container. And as you can see, there's no container running. And unlike before, I'm going to rerun the same command, but this time I'm going to map the directory, my local directory, into Jenkins home. Okay, so this time it's fully up and running, and if I refresh my Jenkins page, instead of going to the initial page where we are asked to enter the initial admin password, I'm actually asked to log in. So I'm going to log in with the user that I created, and once I log in, I'm able now to see the test job that I created before. So that shows that all the custom data that is being generated by the Docker container is actually stored locally on my Docker host. And so every time I run a new instance of Jenkins, I could just map that folder, and all the configuration data will be picked up by Jenkins when it runs the Docker container. So that shows how to map a port and how to map a volume on an actual Docker container. It's a real-life example of using Docker with Jenkins. So that's about it for now. Thank you very much for your time, and see you in the next lecture. Hello and welcome to this lecture on Docker images. In this lecture, we're going to see how to create your own image. Now, before that, why would you need to create your own image? It could either be because you cannot find a component or a service that you want to use as part of your application on Docker Hub already, or you and your team decided that the application you're developing will be Dockerized for ease of shipping and deployment. In this case, I'm going to containerize an application, a simple web application that I have built using the Python Flask framework. First, we need to understand what we are containerizing, or what application we are creating an image for, and how the application is built. So start by thinking what you might do if you want to deploy the application manually. We write down the steps required in the right order. I'm creating an image for a simple web application. If I were to set it up manually, I would start with an operating system like Ubuntu, then update the source repositories using the apt command, then install dependencies using the apt command, then install Python dependencies using the pip command, then copy over the source code of my application to a location like opt, and then finally run the web server using the flask command. Now that I have the instructions, create a Docker file using these. Here's a quick overview of the process of creating your own image. First, create a Docker file named Dockerfile and write down the instructions for setting up your application in it, such as installing dependencies, where to copy the source code from and to, and what the entry point of the application is, etc. Once done, build your image using the docker build command and specify the Docker file as input, as well as a tag name for the image. This will create an image locally on your system. To make it available on the public Docker Hub registry, run the docker push command and specify the name of the image you just created. In this case, the name of the image is my account name, which is Shad, followed by the image name, which is my custom app. Now let's take a closer look at that Docker file. Docker file is a text file written in a specific format that Docker can understand. It's in an instruction and arguments format. For example, in this Docker file, everything on the left in caps is an instruction. In this case, from, run, copy, and entry point are all instructions. Each of these instruct Docker to perform a specific action while creating the image. Everything on the right is an argument to those instructions. The first line from Ubuntu defines what the base OS should be for this container. Every Docker image must be based off of another image, either an OS or another image that was created before based on an OS. You can find official releases of all operating systems on Docker Hub. It's important to note that all Docker files must start with a from instruction. The run instruction instructs Docker to run a particular command on those base images. So at this point, Docker runs the apt get update command to fetch the updated packages and installs required dependencies on the image. Then the copy instruction copies files from the local system onto the Docker image. In this case, the source code of our application is in the current folder, and I'll be copying it over to the location opt source code inside the Docker image. And finally, entry point allows us to specify a command that will be run when the image is run as a container. When Docker builds the images, it builds these in a layered architecture. Each line of instruction creates a new layer in the Docker image with just the changes from the previous layer. For example, the first layer is a base Ubuntu OS, followed by the second instruction that creates a second layer which installs all the apt packages, and then the third instruction creates a third layer with the Python packages, followed by the fourth layer that copies the source code over, and the final layer that updates the entry point of the image. Since each layer only stores the changes from the previous layer, it is reflected in the size as well. If you look at the base Ubuntu image, it is around 120 MB in size. The apt packages that I install is around 300 MB, and the remaining layers are small. You could see this information if you run the docker history command followed by the image name. When you run the docker build command, you could see the various steps involved and the result of each task. All the layers built are cached, so the layered architecture helps you restart docker build from that particular step in case it fails, or if you were to add new steps in the build process, you wouldn't have to start all over again. All the layers built are cached by Docker. So in case a particular step was to fail, for example, in this case, step 3 failed, and you were to fix the issue and rerun docker build, it will reuse the previous layers from cache and continue to build the remaining layers. The same is true if you were to add additional steps in the Docker file. This way, rebuilding your image is faster, and you don't have to wait for Docker to rebuild the entire image each time. This is helpful especially when you update source code of your application, as it may change more frequently. Only the layers above the updated layers needs to be rebuilt. We just saw a number of products containerized, such as databases, development tools, operating systems, etc. But that's just not it. You can containerize almost all of the application, even simple ones like browsers or utilities like curl, applications like Spotify, Skype, etc. Basically, you can containerize everything. And going forward, I see that's how everyone is going to run applications. Nobody is going to install anything anymore going forward. Instead, they're just going to run it using Docker. And when they don't need it anymore, get rid of it easily without having to clean up too much. Hello and welcome to this demo. In this demo, I'd like to show how to create our own Docker image for an application that we have. So first I'm going to explain a little bit about my application. So I have a simple web application which is based on Python Flask. It's on my GitHub page. It's a really simple application that just prints a message onto the screen. So how do you actually deploy this application? So there are some dependencies first. For example, there are some Python dependencies, and then you install the web application dependencies like Flask and the Flask MySQL Python dependencies. And then you basically run your application using the Flask command. And finally, just go to the once it's up and running, go to the website, go to the browser and access the IP of the host where it's running on, and go to the 5000 port, and you'll see a welcome message. So it's a simple application. If you ask how are you, it's going to come back saying I'm good. How about you? I'm going to show the code. It's just one single app.py file, and if you look at this file, all you have is a simple root, which is the default root that returns welcome message, and then another URL, how are you, that returns another message. So it's a really simple web application. So first I'm just going to show how to deploy it manually. So what I would like to do is I don't want to install anything on my Docker host. I just want to keep it clean. I don't want to install some dependencies now and then remove it later. So since I have Docker already, the easiest way to go about this is to start with some kind of a base operating system. Okay, so I'd like to start with the base operating system like Ubuntu, since I already have it, the image pulled. So I could run a docker run Ubuntu, but what I want to do is I want it to stay alive, and I want to work on it, work on that particular container. So I'm going to append a bash command, so it runs the bash command when it starts the container, and I'm going to map the standard input using the -i parameter and the terminal using the T. So this way, as soon as the Ubuntu image starts, and it runs the bash command, and it takes or it attaches my input and terminal to that particular container. So that basically runs the command, runs the container, and connects me onto that particular container, which is all I want for now. And as soon as I exit the container, the image is going to stop. So this is all I want for now, just to play around and test my application. So I have my Ubuntu image running, and what I'm going to do is I'm going to follow instructions in setting up my simple web application. So the first thing to do is install Python. So I'm not going to install the remaining dependencies there. I'm just going to install Python. So I'm going to run apt-get install Python. It cannot locate the package Python. That's because we have it run the apt-get update to update the package index. Okay, so I've run that, and now I'm going to run and try and install Python. Okay, so it's installed Python, and if I run Python command, I can see that Python 2.7 is installed, which is good. Okay, so I'm good with that. So the next step is to install Flask. So I'm going to use pip install Flask. So pip is not found, so I need to install pip first. So I'm going to do apt-get install Python pip. Okay, so pip is installed, and I'm now going to install the Flask dependency for my web application using pip. Okay, so that's installed and it's successful. So I can now run my web server using the Flask run command, but for that I need the source code, of course. So I go to my source code, and all I'm going to do is I'm just going to copy the source code of the application and create it here. So I'm going to put the source code in /opt/app.py. I'm going to paste the source code there. I'm going to follow the instructions here to run the application, which is this. I'm just going to copy that and run it. Okay, so it's inside OPT folder, so I'm going to go there, and I'm going to run that again. So as you can see, my Flask application is currently running. Now, how do I access my web server? So if you remember, when I ran the Docker container using the docker run command, I haven't actually mapped a port to my Docker host. And so the only way to access my application is to go in to the host and access it from a web browser inside my host. So I'm going to go here, and I'm going to go into the 172.17.0.2 IP, and I'm going to access the port 5000 because it's 5000 on which my web server is listening. And when I run that, I can actually see the welcome message come right here, and you can actually see some output here as well. Another URL that we talked about was how are you. So I'm just going to say how are you in the URL, and it's come back with the message, I'm good, how about you. So that's working. So my application is working. So this is how I set up my simple web application. Now, how do I Dockerize it? Let's go back. I'm going to quit the application. I'm going to I've actually got the instructions ready. So the first thing to do is whatever you need to containerize, first go over the basic install steps. So try to do it once manually, and then note down the steps required. So what I'm going to do is I'm going to open a notepad, and write down the steps that I followed. For example, the first thing that I did is apt get update. So I'm just going to run the history command and pull down all the instructions from that. And then I ran the apt get install Python. And then I ran pip install Flask, but I had to have Python pip for that. So I'm going to copy pip from here. So this is going to be my next command. And then followed by pip install Flask. And then I created my application file at app.py. So I'm just going to write it down here, create or copy application code to opt app.py. And then finally I ran my Flask application using this command. And this should actually be opt app.py. Okay, so this is all that I need to install and set up and run my application on a new host, on an Ubuntu host. So I have the instructions ready. So what I'm going to do is I'm going to exit out of this container and back to my Docker container. I'm going to run docker ps, and I see there are no containers running. So as we saw in the lecture, the first thing to do is to create a Docker file. So I'm just, before that, I'm going to create a directory called my custom app. All right, I'll say my symbol web app. And I'll create all the files, all the Docker files inside this particular directory. So the first thing that I need to create is a Docker file. So I'll call it Docker file. And what I did here is, if I look at my instructions, the first thing is before I run the update command, as we saw in the instructions in the lecture, the first instruction should always be from. So I'm going to start from an Ubuntu based operating system. Okay, so I have the instructions here, and I have my Docker file here. So I'm going to start with Ubuntu, and then I'm going to run the apt get update command, apt get update. Then I'm going to run apt get install -y. -y is required, so it doesn't actually wait there waiting for your prompt. And then I could do both in this command. I could install Python and python-pip in the same command. And then I need to run the Flask, installing the Flask dependency. So I do pip install Flask. And then this is where I need to copy my source code of the application from my local directory to the Docker container. So I use the copy instruction, and then I say copy app.py. So this would mean this is assuming that I have my app.py in my local directory, which I don't have for now, but as soon as I finish creating the Docker file, that's what I would do next. So I have my app.py, and then I want it to be copied to opt app.py inside the Docker container. And then finally, the application, the code to run the application, that would go in entry point. So I'd say entry point is, and just copy the command to run my application. So that's basically it. Before I try to build it, I need my application code in the same directory. So I'm going to create a app.py here and copy the application source code. So I'm all set. I could now run the docker build command. So I do a docker build dot, and it's going to start building the image. So I already have Ubuntu, so the step 1 out of 6 was completed immediately because it didn't have to go out and pull the image. Step 2 is running apt get update, and that's, you can see the output of that particular step right here. Similarly, you will be able to see output of all the instructions on the screen. Okay, so it's finished building my image, and as you can see, all the steps are complete. Step 5 out of 6, 6 out of 6 is complete, and finally it successfully built my image. So if you look at the command, I haven't actually specified a name for the image, so I'm just going to run it again, and I'm going to give a tag. I'm going to say my simple web app, and now since it's already built, it's just going to go through that real quick because it doesn't have to rebuild the whole image again. As we discussed in the lecture, whenever Docker builds an image, it builds and caches each layer. So all the layers are cached, and I don't really have to, even if I rebuild the image without any changes, it's just going to build real quick, and it's not actually going to go through the whole build process. So now I have my new image. So if I just clear my screen and run a Docker image, Docker images, I can see my new image right here. And so what I'm going to do is I'm just going to run that by running the Docker run and providing my simple web app. And as you can see, it started and it's listening on 5,000. So if I go inside my host, and if I go to that particular URL, I should be able to see that it's listening and it's working. Okay, so that's good, and I could also map a port and access it from my Docker host. Okay, so I have my simple web app image. Now, how do I push it to the Docker hub and make it available to the public? So once I have my application ready, I could push it to the Docker hub by running the docker push command. Now before that, you should have tagged your application with your repository. So if you do a docker push my simple web app, it says requested access to the resource is denied. The reason is by default, if you didn't specify an organization in your name, it's going to try and push it to the default organization, which is called library, or the default account, which is the library, and not everybody has the permission to push it to that account. That's only for default Docker supported official repositories. So you can only push to repositories under your own account. So first what we need to do is we need to build the image and tag it with our not just the name directly, but you need to tag it with your account name. So you're going to do a docker build once again, and in this time you're going to tag it with your account name. In this case, my name is Mumshad, and you're going to tag it with your application name. Okay, so if I do a docker images, I can see that I've created a new image, and then now I do a docker push and provide that repository name, the image name. It says requested access to the resources denied if you haven't logged in. So there's a prerequisite, which is to log in. So you do a docker login first, provide your user account. So my user account is this, and I'm going to type in my password, and login succeeded. Okay, so that's good. Now if I run the push command again, it will push my image to the Docker hub. Okay, so my application is now pushed to the Docker hub. So if I go to Docker hub and if I go to my dashboard, if I'm logged in with the user, I will now be able to see my application right there. So if I look at the bottom, I see my simple web app, and if you go inside it, you should be able to see, and you have the command here on how to pull and run this particular application. That's about it. That's available now on public, and if you actually want to make it private, you can actually do that, but with your free account on Docker Hub, you can only have one of private repositories. Okay, so once it's there, any user anywhere in the world can actually pull down your image, your container, and run your application with a simple docker run command. Okay, so that's about it. In this demo, we looked at how to create our own simple Docker image. So go ahead and practice for yourself, create your own images, containerize your applications, and push them to Docker Hub. Thank you very much for your time, and we will meet in the next lecture. Let us start with a simple web application written in Python. This piece of code is used to create a web application that displays a web page with a background color. If you look closely into the application code, you will see a line that sets the background color to red. Now, that works just fine. However, if you decide to change the color in the future, you will have to change the application code. It is a best practice to move such information out of the application code and into, say, an environment variable called app_color. The next time you run the application, set an environment variable called app_color to a desired value, and the application now has a new color. Once your application gets packaged into a Docker image, you would then run it with the docker run command followed by the name of the image. However, if you wish to pass the environment variable as we did before, you would now use the docker run command's -e option to set an environment variable within the container. To deploy multiple containers with different colors, you would run the docker command multiple times and set a different value for the environment variable each time. So how do you find the environment variable set on a container that's already running? Use the docker inspect command to inspect the properties of a running container. Under the config section, you will find the list of environment variables set on the container. Well, that's it for this lecture on configuring environment variables in Docker. In this lecture, we will look at commands, arguments, and entry points in Docker. Let's start with a simple scenario. Say you were to run a Docker container from an Ubuntu image. When you run the docker run Ubuntu command, it runs an instance of Ubuntu image and exits immediately. If you were to list the running containers, you wouldn't see the container running. If you list all containers, including those that are stopped, you will see that the new container you ran is in an exited state. Now, why is that? Unlike virtual machines, containers are not meant to host an operating system. Containers are meant to run a specific task or process, such as to host an instance of a web server or application server or a database, or simply to carry out some kind of computation or analysis. Once the task is complete, the container exits. A container only lives as long as the process inside it is alive. If the web service inside the container is stopped or crashes, the container exits. So who defines what process is run within the container? If you look at the Docker file for popular Docker images like nginx, you will see an instruction called cmd, which stands for command, that defines the program that will be run within the container when it starts. For the nginx image, it is the nginx command. For the MySQL image, it is the mysqld command. What we tried to do earlier was to run a container with a plain Ubuntu operating system. Let us look at the Docker file for this image. You will see that it uses bash as the default command. Now, bash is not really a process like a web server or database server. It is a shell that listens for inputs from a terminal. If it cannot find a terminal, it exits. When we ran the Ubuntu container earlier, Docker created a container from the Ubuntu image and launched the bash program. By default, Docker does not attach a terminal to a container when it is run. And so the bash program does not find a terminal, and so it exits. Since the process that was started when the container was created finished, the container exits as well. So how do you specify a different command to start the container? One option is to append a command to the Docker run command, and that way it overrides the default command specified within the image. In this case, I run the docker run Ubuntu command with the sleep5 command as the added option. This way, when the container starts, it runs the sleep program, waits for 5 seconds, and then exits. But how do you make that change permanent? Say you want the image to always run the sleep command when it starts. You would then create your own image from the base Ubuntu image and specify a new command. There are different ways of specifying the command. Either the command simply as is in a shell form or in a JSON array format like this. But remember, when you specify in a JSON array format, the first element in the array should be the executable. In this case, the sleep program. Do not specify the command and parameters together like this. The command and its parameters should be separate elements in the list. So I now build my new image using the docker build command and name it as Ubuntu Sleeper. I could now simply run the docker Ubuntu Sleeper command and get the same results. It always sleeps for 5 seconds and exits. But what if I wish to change the number of seconds it sleeps? Currently, it is hard-coded to 5 seconds. As we learned before, one option is to run the docker run command with the new command appended to it, in this case, sleep10. And so the command that will be run at startup will be sleep10. But it doesn't look very good. The name of the image, Ubuntu Sleeper, in itself implies that the container will sleep. So we shouldn't have to specify the sleep command again. Instead, we would like it to be something like this. Docker run Ubuntu Sleeper 10. We only want to pass in the number of seconds the container should sleep, and the sleep command should be invoked automatically. And that is where the entry point instruction comes into play. The entry point instruction is like the command instruction, as in you can specify the program that will be run when the container starts. And whatever you specify on the command line, in this case 10, will get appended to the entry point. So the command that will be run when the container starts is sleep10. So that's the difference between the two. In case of the CMD instruction, the command line parameters passed will get replaced entirely, whereas in case of entry point, the command line parameters will get appended. Now, in the second case, what if I run the Ubuntu Sleeper image command without appending the number of seconds? Then, the command at startup will be just sleep, and you get the error that the operand is missing. So how do you configure a default value for the command if one was not specified in the command line? That's where you would use both entry point as well as the command instruction. In this case, the command instruction will be appended to the entry point instruction. So at startup, the command would be sleep5 if you didn't specify any parameters in the command line. If you did, then that will override the command instruction. And remember, for this to happen, you should always specify the entry point and command instructions in a JSON format. Finally, what if you really want to modify the entry point during runtime? Say, from sleep to an imaginary sleep 2.0 command. Well, in that case, you can override it by using the entry point option in the docker run command. The final command at startup would then be sleep 2.0 10. Well, that's it for this lecture, and I will see you in the next. Hello and welcome to this lecture on Docker Compose. Going forward, we will be working with configurations in YAML file. so it is important that you are comfortable with YAML. Let's recap a few things real quick. Of course, we first learned how to run a Docker container using the docker run command. If we needed to set up a complex application running multiple services, a better way to do it is to use Docker Compose. With Docker Compose, we could create a configuration file in YAML format called dockercompose.yaml and put together the different services and the options specific to running them in this file. Then we could simply run a docker compose up command to bring up the entire application stack. This is easier to implement, run, and maintain as all changes are always stored in the docker compose configuration file. However, this is all only applicable to running containers on a single Docker host. And for now, don't worry about the YAML file. We will take a closer look at the YAML file in a bit and see how to put it together. That was a really simple application that I put together. Let us look at a better example. I'm going to use the same sample application that everyone uses to demonstrate Docker. It's a simple yet comprehensive application developed by Docker to demonstrate the various features available in running an application stack on Docker. So let's first get familiarized with the application, because we will be working with the same application in different sections through the rest of this course. This is a sample voting application which provides an interface for a user to vote and another interface to show the results. The application consists of various components such as the voting app, which is a web application developed in Python to provide the user with an interface to choose between two options, a cat and a dog. When you make a selection, the vote is stored in Redis. For those of you who are new to Redis, Redis in this case serves as a database in memory. This vote is then processed by the worker, which is an application written in .NET. The worker application takes the new vote and updates the persistent database, which is a Postgres SQL in our case. The Postgres SQL simply has a table with the number of votes for each category, cats and dogs. In this case, it increments the number of votes for cats as our vote was for cats. Finally, the result of the vote is displayed in a web interface, which is another web application developed in Node.js. This resulting application reads the count of votes from the Postgres SQL database and displays it to the user. So that is the architecture and data flow of this simple voting application stack. As you can see, this sample application is built with a combination of different services, different development tools, and multiple different development platforms such as Python, Node.js, .NET, etc. This sample application will be used to showcase how easy it is to set up an entire application stack consisting of diverse components in Docker. Let us keep aside Docker Swarm, services, and stacks for a minute and see how we can put together this application stack on a single Docker engine using first Docker run commands and then Docker Compose. Let us assume that all images of applications are already built and are available on Docker repository. Let us start with the data layer. First, we run the Docker run command to start an instance of Redis by running the Docker run Redis command. We will add the -d parameter to run this container in the background, and we will also name the container Redis. Now, naming the containers is important. Why is that important? Hold that thought. We will come to that in a bit. Next, we will deploy the Postgres SQL database by running the Docker run Postgres command. This time too, we will add the -d option to run this in the background and name this container DB for database. Next, we will start with the application services. We will deploy a front-end app for voting interface by running an instance of voting app image. Run the Docker run command and name the instance vote. Since this is a web server, it has a web UI instance running on port 80. We will publish that port to 5000 on the host system so we can access it from a browser. Next, we will deploy the result web application that shows the results to the user. For this, we deploy a container using the result-app image and publish port 80 to port 5001 on the host. This way, we can access the web UI of the resulting app on a browser. Finally, we deploy the worker by running an instance of the worker image. Okay, now this is all good, and we can see that all the instances are running on the host. But there is some problem. It just does not seem to work. The problem is that we have successfully run all the different containers, but we haven't actually linked them together. As in, we haven't told the voting web application to use this particular Redis instance. There could be multiple Redis instances running. We haven't told the worker and the resulting app to use this particular PostgreSQL database that we ran. So how do we do that? That is where we use links. Link is a command line option which can be used to link two containers together. For example, the voting app web service is dependent on the Redis service. When the web server starts, as you can see in this piece of code on the web server, it looks for a Redis service running on host Redis. But the voting app container cannot resolve a host by the name Redis. To make the voting app aware of the Redis service, we add a link option while running the voting app container to link it to the Redis container, adding a -- link option to the docker run command and specifying the name of the Redis container, which in this case is Redis, followed by a colon and the name of the host that the voting app is looking for, which is also Redis in this case. Remember that this is why we named the container when we ran it the first time, so we could use its name while creating a link. What this is in fact doing is it creates an entry into the etc host file on the voting app container, adding an entry with the host name Redis with the internal IP of the Redis container. Similarly, we add a link for the result app to communicate with the database by adding a link option to refer the database by the name DB. As you can see in this source code of the application, it makes an attempt to connect to a Postgres database on host DB. Finally, the worker application requires access to both the Redis as well as the Postgres database. So we add two links to the worker application, one link to link the Redis and the other link to link Postgres database. Note that using links this way is deprecated and the support may be removed in future in Docker. This is because, as we will see in some time, advanced and newer concepts in Docker Swarm and networking supports better ways of achieving what we just did here with links. But I wanted to mention it anyway so you learn the concept from the very basics. Once we have the Docker run commands tested and ready, it is easy to generate a Docker Compose file from it. We start by creating a dictionary of container names. We will use the same name we used in the Docker run commands. So we take all the names and create a key with each of them. Then under each item, we specify which image to use. The key is the image and the value is the name of the image to use. Next, inspect the commands and see what are the other options used. We published ports. So let's move those ports under the respective containers. So we create a property called ports and list all the ports that you would like to publish under that. Finally, we are left with links. So whichever container requires a link, create a property under it called links and provide an array of links such as Redis or DB. Note that you could also specify the name of the link this way without the semicolon and the target name. And it will create a link with the same name as the target name. Specifying the DB:DB is similar to simply specifying DB. We will assume the same value to create a link. Now that we're all done with our Docker Compose file, bringing up the stack is really simple. Run the Docker Compose up command to bring up the entire application stack. When we looked at the example of the sample voting application, we assumed that all images are already built. Out of the 5 different components, 2 of them, Redis and Postgres images, we know are already available on Docker Hub. They are official images from Redis and Postgres. But the remaining 3 are our own application. It is not necessary that they are already built and available in a Docker registry. If we would like to instruct Docker Compose to run a Docker build instead of trying to pull an image, we could replace the image line with a build line and specify the location of a directory which contains the application code and a Docker file with instructions to build the Docker image. In this example, for the voting app, I have all the application code in a folder named vote, which contains all application code and a Docker file. This time, when you run the Docker Compose up command, it will first build the images, give a temporary name for it, and then use those images to run containers using the options you specified before. Similarly, use build option to build the 2 other services from the respective folders. We will now look at different versions of Docker Compose file. This is important because you might see Docker Compose files in different formats at different places and wonder why some look different. Docker Compose evolved over time and now supports a lot more options than it did in the beginning. For example, this is the trimmed down version of the Docker Compose file we used earlier. This is in fact the original version of Docker Compose file known as version 1. This had a number of limitations. For example, if you wanted to deploy containers on a different network other than the default bridge network, there was no way of specifying that in this version of the file. Also, say you have a dependency or startup order of some kind. For example, your database container must come up first and only then should the voting application be started. There was no way you could specify that in the version 1 of the Docker Compose file. Support for these came in version 2. With version 2 and up, the format of the file also changed a little bit. You no longer specify your stack information directly as you did before. It is all encapsulated in a services section. So create a property called services in the root of the file and then move all the services underneath that. You will still use the same Docker Compose up command to bring up your application stack. But how does Docker Compose know what version of the file you're using? You're free to use version 1 or version 2 depending on your needs. So how does the Docker Compose know what format you are using? For version 2 and up, you must specify the version of Docker Compose file you're intending to use by specifying the version at the top of the file. In this case, version:2. Another difference is with networking. In version 1, Docker Compose attaches all the containers it runs to the default bridged network, and then use links to enable communication between the containers as we did before. With version 2, Docker Compose automatically creates a dedicated bridged network for this application and then attaches all containers to that new network. All containers are then able to communicate to each other using each other's service name. So you basically don't need to use links in version 2 of Docker Compose. You can simply get rid of all the links you mentioned in version 1 when you convert a file from version 1 to version 2. And finally, version 2 also introduces a depends on feature. If you wish to specify a startup order, for instance, say the voting web application is dependent on the Redis service. So you need to ensure that Redis container is started first and only then the voting web application must be started. We could add a depends on property to the voting application and indicate that it is dependent on Redis. Then comes version 3, which is the latest as of today. Version 3 is similar to version 2 in the structure, meaning it has a version specification at the top and a services section under which you put all your services, just like in version 2. Make sure to specify the version number as 3 at the top. Version 3 comes with support for Docker Swarm, which we will see later on. There are some options that were removed and added. To see details on those, you could refer to the documentation section using the link in the reference page following this lecture. We will see version 3 in much detail later when we discuss about Docker stacks. Let us talk about networks in Docker Compose. Getting back to our application, so far we've been just deploying all containers on the default bridged network. Let us say we modify the architecture a little bit to contain the traffic from the different sources. For example, we would like to separate the user-generated traffic from the application's internal traffic. So we create a front-end network dedicated for traffic from users and a back-end network dedicated for traffic within the application. We then connect the user-facing applications, which are the voting app and the result app, to the front-end network, and all the components to an internal back-end network. So back in our Docker Compose file, note that I have actually stripped out the port section for simplicity's sake. They're still there, but they're just not shown here. The first thing we need to do if we were to use networks is to define the networks we are going to use. In our case, we have two networks, front-end and back-end. So create a new property called networks at the root level adjacent to the services in the Docker Compose file and add a map of networks we are planning to use. Then, under each service, create a networks property and provide a list of networks that service must be attached to. In case of Redis and DB, it's only the backend network. In case of the front-end applications, such as the voting app and the result app, they require to be attached to both a front-end and back-end network. You must also add a section for worker container to be added to the back-end network. I have just omitted that in this slide due to space constraints. Now that you have seen Docker Compose files, head over to the coding exercises and practice developing some Docker Compose files. That's it for this lecture, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at the example voting app. The example voting app is available in GitHub under the Docker samples repository, and it is available at example-voting app. I will add a link to this in the resources section. In this demo, we're going to look at the architecture of this. We're going to look at the source code a little bit, understand how it's put together, and we will try and deploy this application using Docker. But to start with, we're just going to deploy this application with Docker run, just to make it really simple. And then in the next demos, we'll try to use Docker Compose, and going forward, we'll use Docker Stack and services to deploy it on Swarm. So as a first step, let's try and just understand the application. So the source code is available on GitHub, and you can see basic documentation here. If you look at the architecture, as we discussed in the lecture, you have a voting app which is based in Python, and then you have a Redis messaging system. The vote is cast and it goes to the worker, which is based on .NET, and then the vote is updated in a Postgres database, and then finally the result is displayed in a Node.js based result web application. Out of these, two of the components are Redis and Postgres, so we don't have to worry about that. The three other
components are the applications that we develop. So there are 3 folders in this code repository. We'll first look at the voting app. So if you click on the vote directory, you will be able to see the source code of it, and it's a Python based application. So you have the app.py with the Python code in it. If you open the Python code, it's a Flask based application. It's a very simple application. It has a post and a get request. The get request sends an index.html, which shows the actual web page where a user can cast a vote. And when the user casts a vote, it comes to this post section, and that is where it establishes a connectivity to Redis and tries to store the vote information in Redis. So that's all that this particular voting application is. One thing to take note here is the host that it tries to connect to. It tries to connect to a host named Redis. Okay, now alongside the code, we also have the Docker file. So it creates it from a Python 2.7 Alpine image, and then sets the working directory to app, installs the Python requirements, and the next step is where it copies the application code into the app folder, and finally the entry point for the application. Next, we will take a look at the worker. So go to the worker folder, and the source code of the application is under the main Java worker folder, and there's a worker.java. If you look at this code, this is a .NET based application. So at the top, it tries to connect to the Redis and the Postgres database, and there's a while loop where it waits for the votes from Redis, and whenever a vote is cast and is available in Redis, it takes that vote and updates the table in the Postgres database. If you're interested, go through and take a look at the remainder of the code. We will then look at the Docker file. So the Docker file is based on Microsoft.NET SDK, and that is where it adds the source code of the application to the worker folder, and finally updates the command required to start the worker. Next, we will look at the resulting app, which is based in Node.js. So that is under the result folder, and open the server.js. This is an Express based server, and you can see the source code for that. And all this does is it establishes a connectivity to the Postgres database, and as you can see, the Postgres database host that it tries to connect to is DB. So that's the host name that it tries to connect to. And then it reads the database and reads the values from the database and displays that on the UI. And if you look at the Docker file for that, it starts from the Docker image, starts from a Node.js slim image, and then adds the package.json, which has the dependencies, runs npm install to install those dependencies, copies the source code over, and finally specifies the node server.js command that is to be run when the application starts. And then there are also, in the source code repository, there are also some Docker Compose and Docker Stack files, but we will not look at that right now. We will be creating those ourselves, so we will just ignore that. So what we're going to do now is we'll just go and try and deploy this application ourselves with Docker. But the first thing that we need to do is build these images, because we know that the Redis and Postgres databases already have images available on Docker Hub, but the 3 others are the applications that we are developing, so we do not have images built for those, so we'll have to build them. So I'm going to first clone the source code repository to my local system. So I will do a git clone and then paste the address, and that will clone the source. It is cloned into example voting app, and when I go into example voting app, I have all the code that we just walked through. Okay, so we will start with deploying the voting app. For that, we need to create a Docker image for the voting app. So we will go into the vote directory, and we look at the Docker file. The Docker file looks intact. So we're just going to go ahead and build the Docker image by running the docker build command, and we will tag it with the name voting-app. Okay, so the Docker image is built. If you run the Docker images command, you can see that it has the voting-app image built. So now that I have the voting app image built, I can run a container by running the docker run voting app command, and I'm going to publish a port 5000 to 80. So the container, the voting app container runs on port 80, and I'm going to map that to port 5000 on my host so that I can access it from a browser. So it looks like the container is running. So I'm going to try and open a browser and go to the address with port 5000, and I can see that the web application is displayed, and I can see two options to cast my votes, cats and dogs. Now if I try to cast a vote by clicking on one of the button, you can see it tries to it takes a while, and after a while it fails, and I can now see that there's an internal server error. It says the server encountered an internal error and was unable to complete your request. If I go back and look at the logs, I see that it's failed at the line redis.rpush. So basically it's unable to establish a connectivity to the Redis, obviously because we haven't run a Redis instance. So what we're going to do now is I'm just going to kill that instance, and I will first start a Redis container. So I will run an instance of Redis, and I will name it Redis. So it's pulling down the Redis image, and it's run an instance of Redis. I forgot to run it in the background, so I'll stop that and run it again with the -d for detached option. Okay, so when I tried that, it failed again because I had already run it in the without the detached option. So it already created a container with the name Redis, and I'm trying to create another container with the same name, so it's preventing me from doing that. So I'll have to delete the previously created container. So I'm going to run a docker rm command to delete the previously created container, and I'll run the same command again to start a new instance of Redis. So I now have a Redis instance running. I'm now going to start an instance of my voting app. So I will run the docker run command with the voting app, and I will publish the port 5000. I will also this time add a link to the Redis server. So I'm running a voting app, and I've added a link using the -- link option, and I've specified Redis as we discussed in the lecture. Okay, so it's running now. I'm back to my web portal, and when I try to cast a vote, you see that it goes successfully, and I get a tick mark back. Now this is because my container was now able to establish a connectivity to Redis. So now we have successfully deployed a Redis as well as the voting application. We will now proceed to the worker. And for the worker, a prerequisite is to have a Postgres database. So we will first deploy a Postgres database instance. I'm not very sure what is the version of Postgres that this application requires. So I'm going to go into one of the files here. For example, if I go into the Docker stack file or a Docker compose file, I should be able to find the image that they used. So it's image 9.4. So I'm just going to use that here. I will name the instance DB, and so later on I can use that to create a link. And now, as you can see, it's running. The Postgres database is now started and it's running successfully. I forgot to run it in the background, so I'm just going to kill that, run it in the background. Okay, I hit the issue again about the duplicate name, so I'm just going to delete the one that I created using the docker rm command, and I'm going to rerun the Postgres database in the detached mode. So I now have the Postgres database running. So if I do a docker ps, I see that there are 3 containers running. One is my voting app, one is my Redis, and the third one is the Postgres database. I can now go ahead and deploy the worker. So first I'll have to build the worker. So if I go to the worker directory, I can see the contents of the Docker file, make sure it's intact, and I'm going to run the docker build command to create an to build the Docker image for the worker, and we'll just wait for that to finish. Once that is finished, when we run the docker images command, we are able to see all the images that are available and our newly created worker app image. We will now run an instance of the worker app. Now the worker app needs 2 links. One is to the Redis and another link to the Postgres database. Okay, so it runs, and as soon as it runs, you can see that it's processed 1 vote. So that is the vote that we casted earlier. Okay, so now when I run the docker ps command, I can see that there are 4 containers running. So we have the worker app ready. The next step is to build and deploy the resulting app. So that's the last step. So we will create an image for the result app. We will deploy it and link it to the Postgres database. So we go into the code repository for result, and I have all the application and Docker files there. I will make sure the Docker file is intact, and then I'm going to run the docker build command to create an image for this result app, and I will tag it result-app. So it goes through all the Node.js related installation steps, and finally it's completed. So now I have a new image, which is the result app. I'm now going to run the result app, but it has since it is a web server, it has a port requirement. So it exposes port 80, and that's where it listens. So I'm going to map port 80 to port 5001 because port 5000 on my local host is already occupied by the voting app. So my result app, I'd like to see it on port 5001. So I'll publish the port 80 to 5001, and I also need to add a link because the result app is linked to the DB. So I'll add a link for that. Okay, so that should be it, and I'm now going to hit enter, and I can see that the application has started and it's connected to DB, which is good. And if I go to the web browser and establish a connectivity to port 5001, and I can see the result page. So this is the result page. Since my vote was for cats, I see the 100% votes for cats. I could also go back and change my vote. So if I go back and change my vote to dogs, I see it's changed immediately. So every time I change my vote, it goes through the full cycle. The data goes through Redis, the worker processes it, updates the database, and then it's finally shown in this result page. So that's it for this demo. We took a look at the example voting app. We understood the architecture of it, how it works, and we also successfully deployed it with Docker run commands using links. Thank you very much for your time, and in the next demo we'll look at how to do the same with Docker Compose. Hello and welcome to this demo. In this demo we are going to look at Docker Compose. So we're going to look at how to use Docker Compose to deploy a complex application stack. We're going to use the same example voting application, and we will try and deploy it with Docker Compose. First and foremost, Docker Compose does not get installed by default. When you install Docker on a host, you need to install it separately. So instructions for installing Docker Compose can be found on the Docker documentation site. There are instructions for installing Docker on Mac, Windows, and Linux. And since I'm on Linux, I'm going to follow the instructions in the Linux section. So Docker Compose is simply a script that needs to be run. So all you need to do is use curl and download the Docker Compose file. And once it's downloaded, you set executable permissions to that file, and that should be it. You should have Docker Compose ready to go. Okay, so we have Docker Compose installed. What we're going to look at is first, in the previous demo, we had everything running. So now we're going to first clean up. So we're going to stop all the running containers. So you could run the docker stop command and specify the first 2 digits of all the containers, and it will stop all those containers at once. We can now run the docker ps command to ensure that there are no more containers running. We will now create a Docker Compose file. So we will create a docker compose.yaml file. And the first thing that we'll do is we'll simply start by defining services. So that is what you should do when you start working on a Docker Compose file. Identify all the services required and list them as root properties in the file. So if you look at our architecture diagram, we have a Redis, database, voting app, worker, and result. So I'm going to create an entry for each of them. The first one being Redis. Second one is DB for Postgres database. Third one is vote for voting app. Then worker for worker app, and result for the result app. Okay, now I'm going to edit that file, and I will now add the image specifications. So I will specify the image that should be used to deploy each of these services. Redis uses Redis image, DB uses Postgres database image with a tag of 9.4, Vote uses voting app. I've already built the voting app as part of our previous demo, so I'm just going to reuse that. Worker uses worker app, and result uses result app. So that is good. Next, we need to update port mappings. So I'm going to create a ports property, and under that I'm going to add a list. So the list should be defined using a dash or a hyphen. For the voting app, I'm going to publish port 80 to 5000, and for the result app, I'm going to publish port 80 to 5001, just like what we did in the previous demo. And so there's just one more thing pending, which is the links. So I'm going to add a property for links, and I'm going to link the voting app to Redis, the worker app to Redis and database, and the result app to Postgres database. Okay, so I'm all set. I'm going to save that file, and then I'm going to run the docker compose up command. Okay, so running the docker compose up command now will create all the containers. As you can see, the containers are created with a name, with a prefix root. That is because the current directory that we are in is with the name root. So whichever directory you are in, it uses that directory and prefixes the container names with that directory. As you can see, it's kicked off all the different containers, and all of them are up and running, and I'm now able to access the voting and app and the result page, and I'm able to cast a vote, and I'm able to see the result in the results page. So that's about it for this demo. So thanks a lot for your time, and I will see you in the next lecture.
We will now look at Docker registry. So what is a registry? If the containers were the rain, then they would rain from the Docker registry, which are the clouds. That's where Docker images are stored. It's a central repository of all Docker images. Let's look at a simple nginx container. We run the docker run nginx command to run an instance of the nginx image. Let's take a closer look at that image name. Now, the name is nginx, but what is this image and where is this image pulled from? This name follows Docker's image naming convention. Nginx here is the image or the repository name. When you say nginx, it's actually nginx/nginx. The first part stands for the user or account name. So if you don't provide an account or a repository name, it assumes that it is the same as the given name, which in this case is nginx. The usernames is usually your Docker Hub account name, or if it is an organization, then it's the name of the organization. If you were to create your own account and create your own repositories or images under it, then you would use a similar pattern. Now, where are these images stored and pulled from? Since we have not specified the location where these images are to be pulled from, it is assumed to be on Docker's default registry, Docker Hub, the DNS name for which is docker.io. The registry is where all the images are stored. Whenever you create a new image or update an existing image, you push it to the registry, and every time anyone deploys this application, it is pulled from that registry. There are many other popular registries as well. For example, Google's registry is at gcr.io, where a lot of Kubernetes-related images are stored, like the ones used for performing end-to-end tests on the cluster. These are all publicly accessible images that anyone can download and access. When you have applications built in-house that shouldn't be made available to the public, hosting an internal private registry may be a good solution. Many cloud service providers, such as AWS, Azure, or GCP, provide a private registry by default when you open an account with them. On any of these solutions, be it Docker Hub or Google Registry or your internal private registry, you may choose to make a repository private so that it can only be accessed using a set of credentials. From Docker's perspective, to run a container using an image from a private registry, you first log into your private registry using the Docker login command. Input your credentials. Once successful, run the application using private registry as part of the image name, like this. Now, if you did not log into the private registry, it will come back saying that the image cannot be found. So remember to always log in before pulling or pushing to a private registry. We said that cloud providers like AWS or GCP provide a private registry when you create an account with them. But what if you're running your application on-premise and don't have a private registry? How do you deploy your own private registry within your organization? The Docker registry is itself another application and, of course, is available as a Docker image. The name of the image is registry, and it exposes the API on port 5000. Now that you have your custom registry running at port 5000 on this Docker host, how do you push your own image to it? Use the Docker image tag command to tag the image with the private registry URL in it. In this case, since it's running on the same Docker host, I can use localhost ;5000 followed by the image name. I can then push my image to my local private registry using the command docker push and the new image name with the Docker registry information in it. From there on, I can pull my image from anywhere within this network using either localhost if you're on the same host, or the IP or domain name of my Docker host if I'm accessing from another host in my environment. Well, that's it for this lecture. Head over to the practice test and practice working with private Docker registries. Welcome to this lecture on Docker Engine. In this lecture, we will take a deeper look at Docker's architecture, how it actually runs applications in isolated containers, and how it works under the hood. Docker Engine, as we have learned before, is simply referred to a host with Docker installed on it. When you install Docker on a Linux host, you're actually installing three different components: the Docker daemon, the REST API server, and the Docker CLI. The Docker daemon is a background process that manages Docker objects such as the images, containers, volumes, and networks. The Docker REST API server is the API interface that programs can use to talk to the daemon and provide instructions. You could create your own tools using this REST API. And the Docker CLI is nothing but the command line interface that we've been using until now to perform actions such as running a container, stopping containers, destroying images, etc. It uses the REST API to interact with the Docker daemon. Something to note here is that the Docker CLI need not necessarily be on the same host. It could be on another system, like a laptop, and can still work with a remote Docker engine. Simply use the -h option on the Docker command and specify the remote Docker engine address and a port as shown here. For example, to run a container based on nginx on a remote Docker host, run the command docker-h equals 10.123.2.1:2375 run nginx. Now let's try and understand how exactly are applications containerized in Docker. How does it work under the hoods? Docker uses namespaces to isolate workspace. Process IDs, network, interprocess communication, mounts, and Unix time-sharing systems are created in their own namespace, thereby providing isolation between containers. Let's take a look at one of the namespace isolation technique, process ID namespaces. Whenever a Linux system boots up, it starts with just one process with a process ID of 1. This is the root process and kicks off all the other processes in the system. By the time the system boots up completely, we have a handful of processes running. This can be seen by running the ps command to list all the running processes. The process IDs are unique, and two processes cannot have the same process ID. Now, if we were to create a container, which is basically like a child system within the current system, the child system needs to think that it is an independent system on its own, and it has its own set of processes originating from a root process with a process ID of 1. But we know that there is no hard isolation between the containers and the underlying host. So the processes running inside the container are in fact processes running on the underlying host. And so two processes cannot have the same process ID of 1. This is where namespaces come into play. With process ID namespaces, each process can have multiple process IDs associated with it. For example, when the processes start in the container, it's actually just another set of processes on the base Linux system, and it gets the next available process ID. In this case, 5 and 6. However, they also get another process ID starting with PID1 in the container namespace, which is only visible inside the container. So the container thinks that it has its own root process tree, and so it is an independent system. So how does that relate to an actual system? How do you see this on a host? Let's say I were to run an nginx server as a container. We know that the nginx container runs an nginx service. If we were to list all the services inside the Docker container, we see that the nginx service running with a process ID of 1. This is the process ID of the service inside of the container namespace. If we list the services on the Docker host, we will see the same service but with a different process ID. That indicates that all processes are in fact running on the same host but separated into their own containers using namespaces. So we learned that the underlying Docker host as well as the containers share the same system resources such as CPU and memory. How much of the resources are dedicated to the host and the containers And how does Docker manage and share the resources between the containers? By default, there is no restriction as to how much of a resource a container can use, and hence, a container may end up utilizing all of the resources on the underlying host. But there is a way to restrict the amount of CPU or memory a container can use. Docker uses C groups or control groups to restrict the amount of hardware resources allocated to each container. This can be done by providing the --CPUs option to the Docker run command. Providing a value of 0.5 will ensure that the container does not take up more than 50% of the host CPU at any given time. The same goes with memory. Setting a value of 100M to the --memory option limits the amount of memory the container can use to 100 megabytes. If you're interested in reading more on this topic, refer to the links I posted in the reference page. That's it for now on Docker Engine. In the next lecture, we talk about other advanced topics on Docker storage and file systems. See you in the next lecture.
Hello and welcome to this demo. In this demo, we are going to see namespace process IDs in action. As we discussed in the lecture, we have a Linux system which is a Docker engine, and that has its own root process with a process ID of 1, and that kicked off a set of processes with other process IDs. And on the same Linux host, we have a Docker container which has its own set of processes and its root process with a process ID of 1. As we saw in the lecture, the process in the container which has a root process ID of 1 is in fact just another process running on the underlying Linux system, and that has its own separate process ID, which in this case is 5. So this is what we're going to look at in this demo. We're going to run a container on a Docker host, and we're going to compare the process ID of the same process inside the container as well as outside on the Linux host. So we're going to pick one Docker container. So I'm on Docker Hub, and I'm looking through the available Docker images, and I'm just going to find a web server of some kind. So I'll find Tomcat. So we'll go to Tomcat and we'll look at the instructions for running the image. In this case, I'm just going to select the second command to run the image, because it has a port mapping or publishing as well. So I'm just going to paste that, and I'm going to kick that off, and Tomcat starts up. As you can see, the logs of the Tomcat server starting up. Once it starts up, I'll open a browser and go to the IP of my host and port 8888, and I can see the Apache Tomcat web page. So that confirms that the Docker container is running. So I'm going to stop this container because I didn't actually run it in the background. I wanted to run it in the background, so I just hit Ctrl+C to stop this container, and I'm going to rerun it in the background now. So I'll run the same command with the -D option. Okay, so when I run the docker ps command, I can see that it's the Apache Tomcat server is running, and I can confirm that I can access the web server. Okay, now I'm going to run a command inside the Docker container. So I could use the docker exec command to execute a command inside the Docker container. I will use the ID of the container, which is starting with 5a, and the command I'd like to run is ps-eaf. ps-eaf lists all the processes running on that container. So as you can see, I'm able to see there's just one process running on that container. Since it is a Tomcat container, it's running a Tomcat process, and the process ID, as you can see, is 1. So that's the only process running on the Tomcat container. And if I run the ps-eaf command on my Docker host and grep for the same process, so I'm just going to grep for Docker Java home, just anything from that line, I should be able to see the same process running on my Docker host. But this time you can see that it has a different process ID. So that is telling us that the same process is running inside the Docker container with a process ID of 1, but on the Docker host with a different process ID. So with namespaces, you're able to give multiple process IDs to the same process, thereby making the container think that it is a root process of that particular container, whereas in fact it is just another process running on the underlying Docker host. And containerization technology allows this process to be isolated and run inside a container using namespaces. So it runs with a process ID of 1 inside the container, and outside on the Docker host it runs. It's another process with another process ID. So that's it for this demo. This was a quick demo to show how namespaces are used to isolate containers in the Docker world.
Hello and welcome to this lecture, and we are learning advanced Docker concepts. In this lecture, we're going to talk about Docker storage drivers and file systems. We're going to see where and how Docker stores data and how it manages file systems of the containers. Let us start with how Docker stores data on the local file system. When you install Docker on a system, it creates this folder structure at var lib docker. You have multiple folders under it called AUFS, containers, image, volumes, etc. This is where Docker stores all its data by default. When I say data, I mean files related to images and containers running on the Docker host. For example, all files related to containers are stored under the containers folder, and the files related to images are stored under the image folder. Any volumes created by the Docker containers are created under the volumes folder. Well, don't worry about that for now. We will come back to that in a bit. For now, let's just understand where Docker stores its files and in what format. So how exactly does Docker store the files of an image and a container? To understand that, we need to understand Docker's layered architecture. Let's quickly recap something we learned. When Docker builds images, it builds these in a layered architecture. Each line of instruction in the Docker file creates a new layer in the Docker image with just the changes from the previous layer. For example, the first layer is a base Ubuntu operating system, followed by the second instruction that creates a second layer which installs all the apt packages, and then the third instruction creates a third layer with the Python packages, followed by the fourth layer that copies the source code over, and then finally the fifth layer that updates the entry point of the image. Since each layer only stores the changes from the previous layer, it is reflected in the size as well. If you look at the base Ubuntu image, it is around 120 megabytes in size. The apt packages that I install is around 300 MB, and then the remaining layers are small. To understand the advantages of this layered architecture, let's consider a second application. This application has a different Docker file, but is very similar to our first application, as in it uses the same base image as Ubuntu, uses the same Python and Flask dependencies, but uses a different source code to create a different application, and so a different entry point as well. When I run the docker build command to build a new image for this application, since the first three layers of both the applications are the same, Docker is not going to build the first three layers. Instead, it reuses the same three layers it built for the first application from the cache, and only creates the last two layers with the new sources and the new entry point. This way, Docker builds images faster and efficiently saves disk space. This is also applicable if you were to update your application code. Whenever you update your application code, such as the app.py in this case, Docker simply reuses all the previous layers from cache and quickly rebuilds the application image by updating the latest source code, thus saving us a lot of time during rebuilds and updates. Let's rearrange the layers bottom up so we can understand it better. At the bottom, we have the base Ubuntu layer, then the packages, then the dependencies, and then the source code of the application, and then the entry point. All of these layers are created when we run the docker build command to form the final Docker image. So all of these are the Docker image layers. Once the build is complete, you cannot modify the contents of these layers, and so they are read-only and you can only modify them by initiating a new build. When you run a container based off of this image using the docker run command, Docker creates a container based off of these layers and creates a new writable layer on top of the image layer. The writable layer is used to store data created by the container, such as log files written by the applications, any temporary files generated by the container, or just any file modified by the user on that container. The life of this layer, though, is only as long as the container is alive. When the container is destroyed, this layer and all of the changes stored in it are also destroyed. Remember that the same image layer is shared by all containers created using this image. If I were to log into the newly created container and say, create a new file called temp.txt, it will create that file in the container layer, which is read and write. We just said that the files in the image layer are read-only, meaning you cannot edit anything in those layers. Let's take an example of our application code. Since we bake our code into the image, the code is part of the image layer and as such is read-only. After running a container, what if I wish to modify the source code to say test a change? Remember, the same image layer may be shared between multiple containers created from this image. So does it mean that I cannot modify this file inside the container? No. I can still modify this file, but before I save the modified file, Docker automatically creates a copy of the file in the read-write layer, and I will then be modifying a different version of the file in the read-write layer. All future modifications will be done on this copy of the file in the read-write layer. This is called copy-on-write mechanism. The image layer being read-only just means that the files in these layers will not be modified in the image itself. So the image will remain the same all the time until you rebuild the image using the docker build command. What happens when we get rid of the container? All of the data that was stored in the container layer also gets deleted. The change we made to the app.py and the new temp file we created will also get removed. So what if we wish to persist this data? For example, if we were working with a database and we would like to preserve the data created by the container, we could add a persistent volume to the container. To do this, first create a volume using the docker volume create command. So when I run the docker volume create data_volume command, it creates a folder called data_volume under the var lib docker volumes directory. Then, when I run the Docker container using the docker run command, I could mount this volume inside the Docker container's read-write layer using the -v option like this. So I would do a docker run -v, then specify my newly created volume name followed by a colon and the location inside my container, which is the default location where MySQL stores data, and that is var lib MySQL, and then the image name MySQL. This will create a new container and mount the data volume we created into var lib MySQL folder inside the container. So all data written by the database is in fact stored on the volume created on the Docker host. Even if the container is destroyed, the data is still active. Now, what if you didn't run the docker volume create command to create the volume before the docker run command? For example, if I run the docker run command to create a new instance of MySQL container with the volume data_volume2, which I have not created yet, Docker will automatically create a volume named data_volume2 and mount it to the container. You should be able to see all these volumes if you list the contents of the var lib docker volumes folder. This is called volume mounting, as we are mounting a volume created by Docker under the var lib docker volumes folder. But what if we had our data already at another location? For example, let's say we have some external storage on the Docker host at /data, and we would like to store database data on that volume and not in the default var lib docker volumes folder. In that case, we would run a container using the command docker run-v, but in this case, we will provide the complete path to the folder we would like to mount, that is /data/MySQL. And so it will create a container and mount the folder to the container. This is called bind mounting. So there are two types of mounts, a volume mounting and a bind mount. Volume mount mounts a volume from the volumes directory, and bind mount mounts a directory from any location on the Docker host. One final point to note before I let you go. Using the -v is an old style. The new way is to use -mount option. The --mount is the preferred way as it is more verbose, so you have to specify each parameter in a key equals value format. For example, the previous command can be written with the -mount option as this, using the type, source, and target options. The type in this case is bind, the source is the location on my host, and target is the location on my container. So who is responsible for doing all of these operations? Maintaining the layered architecture, creating a writable layer, moving files across layers to enable copy and write, etc. It's the storage drivers. So Docker uses storage drivers to enable layered architecture. Some of the common storage drivers are AUFS, BTRFS, ZFS, device mapper, overlay, and overlay 2. The selection of the storage driver depends on the underlying OS being used. For example, with Ubuntu, the default storage driver is AUFS, whereas this storage driver is not available on other operating systems like Fedora or CentOS. In that case, device mapper may be a better option. Docker will choose the best storage driver available automatically based on the operating system. The different storage drivers also provide different performance and stability characteristics. So you may want to choose one that fits the needs of your application and your organization. If you would like to read more on any of these storage drivers, please refer to the links in the attached documentation. For now, that is all from the Docker architecture concepts. See you in the next lecture.
Hello and welcome to this demo. In this demo, we're going to look at how Docker stores data in the file system. What is the default folder, or what is the default location where Docker stores data, and how it stores the data and files related to the containers and images and layers that we discussed in the lecture. So when Docker is installed, it automatically creates this folder structure by default at var lib docker. So if you list the contents of /var lib docker, you will be able to see a set of directories created by default. Now, In this case, you can see that there are directories named AUFS, builder, containers, image, network, plugins, swarm, etc. This is the default folder structure maintained by Docker, and Docker automatically places files and creates files and related to images and containers inside these folders. So all the files related to containers are stored inside the containers folder. Files related to image are stored inside the image folder. We also talked about storage drivers. We learned that it is the storage drivers that actually performs all these actions of creating layers and maintaining the layers and the files related to each layer. We also looked at a number of storage drivers that are available with Docker. So let's see what is the storage driver being used in this particular case. So to find that out, run the docker info command. The docker info command lists information about the Docker installed on this particular system. So in this case, as you can see, it shows the Docker version, which is 17.09, and right below that it shows the storage driver being used, and the current storage driver being used is AUFS, and this is the default storage driver for Debian and Ubuntu systems. And right below that you can see the root directory where it stores all the files. So that root directory is var lib docker AUFS. So if you list the contents of that particular directory, var lib docker and AUFS, you will see three other directories that are created, which is diff, layers, and mount. So each storage driver stores data differently. So the way AUFS storage driver stores data is like this, in three different folders called diff, layers, and mount. We will look at what they mean. So if you look at the documentation site for AUFS storage driver, so as you can see, the diff folder is where the actual contents of each layer is stored. A new layer is created for each instruction in the Docker file. So let's say, for example, if one of the instruction in Docker file is to add our source code into the Docker image, then that creates a new layer, and all the source code of our application gets stored in that particular layer. So a layer is just another folder in this case, and it is mapped by the storage driver, and when we add source code of our application into the image, in fact all the source code of the application is copied and placed into this particular layer. So we will see that in a bit. The other two folders are layers and MNT. The layers folder stores metadata about how image layers are stacked, and the mount folder stores information about the mount points. So let's list the contents of the diff folder. So the diff folder currently doesn't have anything because we do not have any images or containers. So none of the three folders have any contents in it. So what we'll do is we'll just pull a sample Docker image, which is the hello world image. So as you might have worked with it before, it's just an image that shows you a message, a hello world message to the user. So I'm going to now pull the hello world image. Okay, so that is done, and when I do a docker images command, it lists the hello world image that I just downloaded. Now when I list the contents of the AUFS diff folder, I can see that there is a directory, and if I go into the directory, I'm able to see a file which is actually the script that runs as part of the hello world container. So the hello world is a simple image which just has one file in it, which is named here as hello, and when it runs, it just prints a message. So since it is just one file that is part of the image, that is all that you can see. So you have a single directory, and you can see that particular file here. Now, if you would like to see how a particular image is built, for example, if you were to download an image from the Docker Hub, and you haven't seen its Docker file, but you'd like to see how that image was built, you could use the Docker history command. So run the Docker history command and specify the image ID, and it'll show you a list of steps that were followed to create that image. In this case, since this is a very simple image, the first step, as you can see at the bottom, is to copy a file. In this case, it's just the hello script that is being copied. So the hello script is being copied into a particular location, and the second instruction that you see above is a command to run that particular script. Now, as we know that it just has a hello script and it just needs to be run. In fact, we could just run that script directly because we now know where that script is placed by Docker. So when Docker pulled the image, it also pulled all the files or any dependencies associated to that particular image. And now that we know the folder structure of Docker, we know where that particular script is stored. So instead of running a Docker container, we could even just run that script directly and we'll see the output. So as you can see the output of that script right here. So this is just a hack. I just wanted to show you where the files are stored by Docker, and we could access them directly from our Docker host. Let us look at a better example. So in this case, we're going to create a Docker image on our own. So I have a sample application here. I have a sample web application. So I'm going into that folder. And as you can see, it's very simple. I just have a Python Flask based web application. The source code of the application is in app.py, and I have a Docker file with instructions on creating the Docker image. So if you look at the Docker file, you can see that it's very simple and there are 5 steps involved. The first step is to create the Docker image from Ubuntu. The second step is to install Python packages. The third step is to install the Python dependencies. The fourth step is to copy our source code into the OPT location. So I'm going to copy app.py from the current location into the Docker image. And the last step is to specify an entry point for the Flask application. So it's very simple. I'm now going to run the docker build command to build our image. Okay, so it goes out and tries to pull down the Ubuntu image because it is not available locally, and then it proceeds to installing the Python dependencies and packages. So this takes a few minutes. Since I'm installing a lot of dependencies, it actually took about 5 minutes or so. So I'm just going to fast forward it here. Okay, so in about 5 minutes, it's finished building the Docker image. As you can see, it went step by step, installed all the dependencies, copied our application source code, and updated the entry point for my application. And you can see the message, successfully built container. So we're good. Okay, now I'm going to list the images. As you can see, my new image is built. There are actually 3 images now. One is the hello world, which we pulled earlier. The other 2 are Ubuntu and an unnamed image. The Ubuntu image was downloaded as part of our previous build because it required Ubuntu. The last one is the image that we actually build right now. But you don't see any name or tag for it because we haven't specified any. So I'm just going to run the docker build command again. So I'm going to run the same docker build command, and this time I'm going to give it a tag with the -t parameter. So I'm going to specify -t and give a name called simple web app. This time it has actually finished pretty quick. The last time it took about 5 minutes, but this time it just took 1 second. Now this is because we ran the same docker build command, but it didn't actually rebuild the entire image because the image was already built. and there were no changes made to either my application code or any of the files associated with it, or my Docker file, or any of the instructions in my Docker file. That is the reason it built it quickly. If you look at it, if you look at the steps, as you can see, the first step, which is pulling the Ubuntu image, since the image is already there, it didn't pull it again. The second step, where it is installing the Python dependencies, since this step was already executed before on the Ubuntu image, it was available in cache, so it just used that particular layer from cache. That is why you see that text there. And then the third step again was done before, which is why you see that it's using it from cache. Again, fourth and fifth step, all of them were done before, which is why you see that they all picked up from cache, and it finished in about a second. If you run the docker images command now, we can see that it has tagged it with the same name. So it's the same image, we rebuilt the same image, but it now tagged it with a new name. Now let's look at the history of this particular new image that we built. Earlier we said that if you could look at the history command to see how a Docker image was built. In this case, you see each instruction in the Docker file is appearing here. So you can actually match each instruction in the Docker file. So the first, the bottommost 4 or 5 layers are in fact Ubuntu. So that particular Ubuntu image is also another Docker image, and it has within it 4 or 5 layers, which is why you are seeing that here. And then each instruction can be seen as a layer, and the respective size for each of that layer is seen here. So as you can see, the Python dependencies are one of the heaviest. It is around 366 MB of those Python dependencies. Let's now go to the var lib docker directory and see if there are any new folders created there. So if you look at the AUFS directory and go into diff, as we said earlier, it is in the diff folder where all the actual contents are stored. Now we can see that there are many more directories created here. Now I could run the du-sh command to list the size of each of these folders. We should be able to look at the size of these folders and compare it to the size of the layers we saw above to try and match these layers and the folders. So as you can see, there's a folder with a size of 376 megabytes, and that is most probably where all the Python related packages and dependencies are installed. And similarly, there's another one with 100 MB. That is where the Ubuntu related files are stored. So what we are interested in here is our application code. So one of the instructions was to copy our application code into the image. So we do not know which folder exactly it is. So we'll just try and look at the folders which have the lowest size. So I'm just going to try each of these. Okay, so the one with the 12K size looks to be it, and there you can see our application code, and if I look at its contents, I'm able to see the contents. So that's the same application file that we used to create the image. So we learned in the lecture about layered architecture. We learned that when we created the first application, it built everything from scratch. But if we had another version of the same application, wherein only our source code changed, so we have a separate Docker file and separate application code, but all the dependencies, the underlying operating system, if they all remain the same, we learned in the lecture that it's going to reuse the layers that are the same and only create new layers for the files that changed. So we'll take a look at that now. So what we're going to do is we're going to go into our application folder and we're going to create a new version of our application. So we already have a simple web app ready, but what we're going to do is we're going to create a copy of our app source code. Okay, and we're going to edit that, and I'm just going to make a minor change I'm going to change welcome to welcome to, and that's all the change that I'm going to do. Since we changed our application file name, we also need to change the Docker file. So we're going to go into the Docker file. I'm going to create a copy of the Docker file first, and then I'm going to go into the Docker file and use the new source code. So as you can see, the first 3 instructions are exactly the same. I'm only going to change the last 2 instructions. Okay, now I'm going to run the docker build command. When you run the docker build command, it by default picks up the file named docker file. But in this case, we have a new Docker file, which is Dockerfile 2. So we're going to specify that file name using the -f parameter. Okay, so the new Docker image is built. Again, if you look at it, it went real quick. It did not take any time at all. And this is because the first 3 layers, as you can see, is being taken from cache. And those were the most time-consuming layers. However, if you look at step 4 and 5, you will see that it does not say that it's using from cache, because those are new instructions. Those have not been executed before, which is why it actually went out and created new layers for those 2 instructions. Now, it is also important to remember that every time a particular step is changed and Docker has to create that particular layer instead of using it from cache, all the steps following that will be recreated. Which means, let's say in this example we have 5 steps. Let's say we have 5 more steps after this, so a total of 10 steps. In our first application, it goes out and builds everything from step 1 to step 10. When we create our second application, the only step that is changing is, let's say, step 4, which is copying the application source code. But every remaining steps from step 6 to step 10, even if they are exactly the same, when we create our second application, it will still go out and recreate all those steps if they are even if they are the same, because one of the steps changed. So caching only works from the top to the step where it changes. As soon as a particular step changes, it recreates images and it stops using anything from cache from that point on, because as soon as one layer changes, we have no guarantee that the remaining layers will be the same. So it just goes out and recreates the remaining layers. So that is important to note. Now you can see that there is a new image, and it's called Sample Web App 2. It should have been Simple Web App 2, but I made a typo. So our first application is Simple Web App, and our new second application is Sample Web App 2. So if you look at the size of the 2 applications, we can see that they both are 467 MB. So they're the same size. Now, if you look at the history of both images, we can see that they have almost the same instructions. So we just learned that all the layers that were previously built are being used from cache. So why are the sizes being shown as the same here? For example, in this case, both the applications are 467 MB, but we know that both of these applications have the same layers. They use the same layers up to step number 3. And they actually have only very minor differences, which in this case is the source code itself, which we know is just a few KBs in size. So then why are they both shown as 467 MBs? So if you run the Docker images command, and the size that you see here is actually the total space for that image, for each image alone. So if you were to take each image and if you were to try and push it somewhere, or if you were to copy it out, then that particular image along with its underlying dependencies, underlying operating system image, which in this case is Ubuntu, the space that is shown there is actually the total space. It is not exactly the consumed space on the disk. So it doesn't actually show you exactly how much space is consumed by that particular image on the disk. It shows you the total space for that image, including all the duplicates. Now, if you wanted to see the actual consumption or disk space consumption of each of these images, then there's another command, and we'll look at that right now. So let's look at the docker images command again, and as we can see, we have 4 images. 2 of them are web applications, and they're around 430 MB in size, and the Ubuntu image is around 120 MB in size. If you wanted to see the actual space consumption on the disk, run the docker system df command. The system df command shows you the actual disk usage of Docker. So if you just run the docker system df command, it'll show you the disk consumption by images, containers, and local volumes. In this case, I have 4 images and they consume a total of 431 MB. So as you can see here, it's actually showing you the total disk usage by images. Now we know that earlier we saw there are 2 images with around 430 MB in size, but those are including duplicates, and this is the actual disk usage without including any duplicates. Now if you wanted to see a breakdown by image, you can actually run the same command with a -v at the end, and this will show you all the images and their space consumption. So if you look at the 2 sample web application, each of them are 431 MB in size, but there's a new column now which is called shared size, and there you can see that that particular size is actually being shared by 2 images. So the whole of 431 MB is being shared by the 2 web applications. And also you can see the unique size for each of them, and when you add up the unique size, you actually get the total disk, the total size on the disk. So that's about it. That's all for this demo, and in this demo, so we looked at how files are stored by storage drivers on the Docker host. What is the default directory where it stores these files, how to see the actual disk space usage using the docker system df command. So thank you very much, and see you in the next lecture.
We now look at networking in Docker. When you install Docker, it creates 3 networks automatically: bridge, null, and host. Bridge is the default network a container gets attached to. If you would like to associate the container with any other network, you specify the network information using the network command line parameter like this. We will now look at each of these networks. The bridge network is a private internal network created by Docker on the host. All containers attached to this network by default, and they get an internal IP address, usually in the range 172.17 series. The containers can access each other using this internal IP if required. To access any of these containers from the outside world, map the ports of these containers to ports on the Docker host, as we have seen before. Another way to access the containers externally is to associate the container to the host network. This takes out any network isolation between the Docker host and the Docker container. Meaning, if you were to run a web server on port 5000 in a web app container, it is automatically accessible on the same port externally without requiring any port mapping as the web container uses the host's network. This would also mean that, unlike before, you will now not be able to run multiple web containers on the same host on the same port, as the ports are now common to all containers in the host network. With the none network, the containers are not attached to any network and doesn't have any access to the external network or other containers. They run in an isolated network. So we just saw the default bridge network with the network ID 172.70.0.1. So all containers associated to this default network will be able to communicate to each other. But what if we wish to isolate the containers within the Docker host? For example, the first two web containers on internal network 172 and the second two containers on a different internal network, like 182. By default, Docker only creates one internal bridge network. We could create our own internal network using the command docker network create and specify the driver, which is bridge in this case, and the subnet for that network followed by the custom isolated network name. Run the docker network ls command to list all networks. So how do we see the network settings and the IP address assigned to an existing container? Run the docker inspect command with the ID or name of the container, and you will find a section on network settings. There, you can see the type of network the container is attached to, its internal IP address, MAC address, and other settings. Containers can reach each other using their names. For example, in this case, I have a web server and a MySQL database container running on the same node. How can I get my web server to access the database on the database container? One thing I could do is to use the internal IP address assigned to the MySQL container, which in this case is 172.70.0.3. But that is not very ideal because it is not guaranteed that the container will get the same IP when the system reboots. The right way to do it is to use the container name. All containers in a Docker host can resolve each other with the name of the container. Docker has a built-in DNS server that helps the containers to resolve each other using the container name. Note that the built-in DNS server always runs at address 127.0.0.11. So how does Docker implement networking? What's the technology behind it? Like, how are the containers isolated within the host? Docker uses network namespaces that creates a separate namespace for each container. It then uses virtual Ethernet pairs to connect containers together. Well, that's all we can talk about it for now. More about these are advanced concepts that we discuss in the advanced course on Docker on CodeCloud. That's all for now. From this lecture on networking, head over to the practice test and practice working with networking in Docker. I will see you in the next lecture. Earlier in this course, we learned that containers share the underlying OS kernel, and as a result, we cannot have a Windows container running on Linux host or vice versa. We need to keep this in mind while going through this lecture, as it's a very important concept and most beginners tend to have an issue with it. So what are the options available for Docker on Windows? There are two options available. The first one is Docker on Windows using Docker Toolbox. And the second one is the Docker Desktop for Windows option. We will look at each of these now. Let's take a look at the first option, Docker Toolbox. This was the original support for Docker on Windows. Imagine that you have a Windows laptop and no access to any Linux system whatsoever, but you would like to try Docker. You don't have access to a Linux system in the lab or in the cloud. What would you do? What I did was to install a virtualization software on my Windows system like Oracle VirtualBox or VMware Workstation and deploy a Linux VM on it, such as Ubuntu or Debian. then install Docker on the Linux VM, and then play around with it. This is what the first option really does. It doesn't really have anything much to do with Windows. You cannot create Windows-based Docker images or run Windows-based Docker containers. You obviously cannot run Linux container directly on Windows either. You're just working with Docker on a Linux virtual machine on a Windows host. Docker, however, provides us with a set of tools to make this easy, which is called as the Docker Toolbox. The Docker Toolbox contains a set of tools like Oracle VirtualBox, Docker Engine, Docker Machine, Docker Compose, and a user interface called Kitematic. This will help you get started by simply downloading and running the Docker Toolbox executable. It will install VirtualBox, deploy a lightweight VM called boot to Docker, which has Docker running in it already, so that you are all set to start with Docker easily and within a short period of time. Now, what about requirements? You must ensure that your operating system is 64-bit, Windows 7 or higher, and that the virtualization is enabled on the system. Now remember, Docker Toolbox is a legacy solution for older Windows systems that do not meet requirements for the newer Docker for Windows option. The second option is the newer option called Docker Desktop for Windows. In the previous option, we saw that we had Oracle VirtualBox installed on Windows and then a Linux system and then Docker on that Linux system. Now, with Docker for Windows, we take out Oracle VirtualBox and use the native virtualization technology available with Windows called Microsoft Hyper-V. During the installation process for Docker for Windows, it will still automatically create a Linux system underneath, but this time it is created on the Microsoft Hyper-V instead of Oracle VirtualBox and have Docker running on that system. Because of this dependency on Hyper-V, this option is only supported for Windows 10 Enterprise or Professional Edition and on Windows Server 2016, because both these operating systems come with Hyper-V support by default. Now here's the most important point. So far, whatever we have been discussing with Docker's support for Windows, it is strictly for Linux containers, Linux applications packaged into Linux Docker images. We're not talking about Windows applications or Windows images or Windows containers. Both the options we just discussed will help you run a Linux container on a Windows host. With Windows Server 2016, Microsoft announced support for Windows containers for the first time. You can now package applications, Windows applications, into Windows Docker containers and run them on Windows Docker host using Docker Desktop for Windows. When you install Docker Desktop for Windows, the default option is to work with Linux containers. But if you would like to run Windows containers, then you must explicitly configure Docker for Windows to switch to using Windows containers. In early 2016, Microsoft announced Windows containers. Now you could create Windows-based images and run Windows containers on a Windows server, just like how you would run Linux containers on a Linux system. Now you can create Windows images, containerize your applications, and share them through the Docker store as well. Unlike in Linux, there are two types of containers in Windows. The first one is a Windows Server container, which works exactly like Linux containers, where the OS kernel is shared with the underlying operating system. To allow better security boundary between containers and to allow kernels with different versions and configurations to coexist, the second option was introduced, known as the Hyper-V isolation. With Hyper-V isolation, each container is run within a highly optimized virtual machine, guaranteeing complete kernel isolation between the containers and the underlying host. Now, while in the Linux world you had a number of base images for Linux systems such as Ubuntu, Debian, Fedora, Alpine, etc., if you remember that is what you specify at the beginning of the Docker file, in the Windows world we have two options, the Windows Server Core and Nano Server. A Nano Server is a headless deployment option for Windows Server which runs at a fraction of size of the full operating system. You can think of this like the Alpine image in Linux. The Windows Server Core, though, is not as lightweight as you might expect it to be. Finally, Windows containers are supported on Windows Server 2016, Nano Server, and Windows 10 Professional and Enterprise Edition. Remember, on Windows 10 Professional and Enterprise Edition only supports Hyper-V isolated containers, meaning, as we just discussed, every container deployed is deployed on a highly optimized virtual machine. Well, that's it about Docker on Windows. Now, before I finish, I want to point out one important fact. We saw two ways of running a Docker container using VirtualBox or Hyper-V. But remember, VirtualBox and Hyper-V cannot coexist on the same Windows host. So if you started off with Docker Toolbox with VirtualBox, and if you plan to migrate to Hyper-V, remember you cannot have both solutions at the same time. There is a migration guide available on Docker documentation page on how to migrate from VirtualBox to Hyper-V. That's it for now. Thank you, and I will see you in the next lecture. Hello and welcome to this demo. In this demo, we're going to look at Docker on Windows. So here I have a Windows Server 2016 that I'm logged into. And first I'm going to install Docker for Windows. For that, I'm going to open a web browser and search for Docker for Windows. The first result that comes up is takes me directly to the link to download Docker for Windows from Docker Store. So when I click on the link to download from Docker Store, I reach this site where I have further information on Docker for Windows. I'm going to click on Get Docker CE for Windows. And as you can see, it begins downloading Docker for Windows. The download is complete, and I'm now going to run the installation package. When I run the installation package, it downloads further dependencies from the internet, and it proceeds with the installation of Docker for Windows. Once the installation is complete, you can see the installation succeeded message. And as you can see, it says you must log out of Windows to complete installation. So I'm going to click on Close and Log Out. So it signs me out, and I'm going to log back in. I've re-established my remote connection to the server, and I'm back in. And now, as you can see in my desktop, I have a new Docker for Windows shortcut. When I click on that shortcut, in the bottom right corner, you can see that Docker is starting. So we'll give it a few seconds for it to start. When I start Docker for Windows, as we discussed in the lecture, Docker for Windows depends on Hyper-V feature. So if Hyper-V feature is not already enabled, it will give you this warning saying Hyper-V feature is not enabled, and it will ask you if you want to enable it for Docker to be able to work properly. If you click OK, it will automatically restart your computer. So I'm going to go ahead and click OK. I'm now going to log back in. And I'm back into my Docker system. I'm going to open a command prompt and run the Docker command. So if I run the Docker version command, I can see the current version of Docker running. So my Windows system runs a Docker client version, and you can see the version of the Docker client, which is 17.06 in this case. And if you look below, it says there's an error during connect. So it's not able to connect to the Docker server. So the way it works is my Windows system where I've installed Docker has a Docker client, and that remotely connects to the Docker server. The Docker server could either be running on the same system or it could be running on a remote system, as we discussed in the lecture. In this case, the error indicates that the Docker client is unable to communicate to Docker server, and this is actually because we haven't given it enough time for the Docker service to start up. So if you look at the bottom right corner, you will see that a message that now says Docker is running. So in fact, we need to wait for that message before we run any Docker related operations. Now when I run the Docker version command, I can see that the client version is at the top and then the server version is below. If you look closely into the server version, you can see the OS architecture, which is Linux in this case. So as we discussed in the lecture, there are two ways of running Docker on Windows. One is with Linux containers, the other is with Windows containers. The default behavior is to run it with Linux containers. So when you install Docker for Windows for the first time, Docker automatically deploys a test VM, which is a Linux VM, and Docker is in fact installed on the Linux VM, and we use a Docker client to connect to the Linux VM running Docker to perform Docker related operations. That is the reason you see the server version is Linux. Now we can run a container from a Docker image. So I'm going to run the Docker run hello world, and it pulls the hello world image, and as you can see the output of the hello world container. We can also run an Ubuntu system, so I'm going to run docker run Ubuntu, and that is going to download the latest Ubuntu image, and I'm inside the Ubuntu system. So that's running Linux containers on a Windows system. It is not really running directly on the Windows system. As we discussed, it's running on a Linux system, which is deployed on the Hyper-V Windows. So if you'd like to see that, you can go to the server manager and go into Hyper-V. If you go into Hyper-V, you see that there is a test VM that is deployed there. If you right click on the test VM and select Hyper-V manager, it will open up Hyper-V manager, and there you can see the test VM, and it is in fact a Moby Linux VM, which is a lightweight Linux VM distribution, and it is on this VM that Docker is in fact running. So all the images that we pull, the Linux containers that are run, are all run in fact on this virtual machine, lightweight virtual machine that's running on Hyper-V. The other option is running Windows-based containers. So with Windows Server 2016 and Windows 10 Professional Edition, you can now run Windows-based containers. However, you need to switch the Docker mode from Linux to Windows. You can do that by right-clicking on the Docker icon in the system tray and selecting Switch to Windows Container. And then you will see the message Docker is switching in the bottom right hand corner, and you will get a message that says containers feature is not enabled. So containers is a feature that comes built in with Windows Server 2016, and if you'd like to work with Windows-based containers, you need this to be enabled. Again, if you click on OK, it will enable containers features and your computer will restart automatically. So I'm going to click on OK, and we'll wait for it to restart, and I will now log back in. Okay, so I'm back into my server. I'll just wait for the Docker to run, so I can see that Docker is running in the bottom right hand corner. So I'm going to open a command prompt, and now when I run the Docker version command, I see the client version up, which is Windows, and this time the server version is also Windows. So that indicates that I'm now working with Docker containers on Windows. I can now run the docker run hello world command, and this time you will see that it takes a little bit more time because the Windows-based images are larger in size when compared to the Linux-based images. So you will see that it takes a while for it to download the hello world image, and once it downloads and it runs, you can see the message, the hello message from the hello world Docker image for Windows. You can also see a command here to run Windows Server Core as a container. So let's copy that command and run that, and so this is going to pull down the Windows Server Core image from Docker store, and we'll run the image and it'll get us into the PowerShell prompt on that particular image. So once the image is downloaded, you can then use that image to create to bake your application into that image and create your own custom application images based on Windows containers. Okay, so it's run and it's downloaded and run the image, and I'm inside my new Docker container for Windows. So that's pretty much it from this demo. Thank you for your time, and I will see you in the next lecture. We now look at Docker on Mac. Docker on Mac is similar to Docker on Windows. There are two options to get started: Docker on Mac using Docker Toolbox or Docker Desktop for Mac option. Let's look at the first option, Docker Toolbox. This was the original support for Docker on Mac. It is Docker on a Linux VM created using VirtualBox on Mac. As with Windows, it has nothing to do with Mac applications or Mac-based images or Mac containers. It purely runs Linux containers on a Mac OS. Docker Toolbox contains a set of tools like Oracle VirtualBox, Docker Engine, Docker Machine, Docker Compose, and a user interface called Kitematic. When you download and install the Docker Toolbox executable, it installs VirtualBox, deploys lightweight VM called boot to Docker, which has Docker running in it already. This requires Mac OS 10.8 or newer. The second option is the newer option called Docker Desktop for Mac. With Docker Desktop for Mac, we take out Oracle VirtualBox and use Hyperkit virtualization technology. During the installation process for Docker for Mac, it will still automatically create a Linux system underneath, but this time it is created on Hyperkit instead of Oracle VirtualBox, and have Docker running on that system. This requires Mac OS Sierra 10.12 or newer, and the Mac hardware must be 2010 or newer model. Finally, remember that all of this is to be able to run Linux container on Mac. As of this recording, there are no Mac-based images or containers. Well, that's it with Docker on Mac for now. We will now try to understand what container orchestration is. So far in this course, we have seen that with Docker, you can run a single instance of the application with a simple docker run command. In this case, to run a Node.js-based application, you run the docker run Node.js command. But that's just one instance of your application on one Docker host. What happens when the number of users increase and that instance is no longer able to handle the load? You deploy additional instance of your application by running the docker run command multiple times. So that's something you have to do yourself. You have to keep a close watch on the load and performance of your application and deploy additional instances yourself. And not just that, you have to keep a close watch on the health of these applications. If a container was to fail, you should be able to detect that and run the docker run command again to deploy another instance of that application. What about the health of the Docker host itself? What if the host crashes and is inaccessible? The containers hosted on that host become inaccessible too. So what do you do in order to solve these issues? You will need a dedicated engineer who can sit and monitor the state, performance, and health of the containers and take necessary actions to remediate the situation. But when you have large applications deployed with tens of thousands of containers, that's not a practical approach. So you can build your own scripts, and that will help you tackle these issues to some extent. Container orchestration is just a solution for that. It is a solution that consists of a set of tools and scripts that can help host containers in a production environment. Typically, a container orchestration solution consists of multiple Docker hosts that can host containers. That way, even if one fails, the application is still accessible through the others. A container orchestration solution easily allows you to deploy hundreds or thousands of instances of your application with a single command. This is a command used for Docker Swarm. We will look at the command itself in a bit. Some orchestration solutions can help you automatically scale up the number of instances when users increase and scale down the number of instances when the demand decreases. Some solutions can even help you in automatically adding additional hosts to support the user load. And not just clustering and scaling, The container orchestration solutions also provide support for advanced networking between these containers across different hosts, as well as load balancing user requests across different hosts. They also provide support for sharing storage between the hosts, as well as support for configuration management and security within the cluster. There are multiple container orchestration solutions available today. Docker has Docker Swarm, Kubernetes from Google, and MezOS from Apache. While Docker Swarm is really easy to set up and get started, it lacks some of the advanced auto-scaling features required for complex production-grade applications. Mesos, on the other hand, is quite difficult to set up and get started, but supports many advanced features. Kubernetes, arguably the most popular of it all, is a bit difficult to set up and get started, but provides a lot of options to customize deployments and has support for many different vendors. Kubernetes is now supported on all public cloud service providers like GCP, Azure, and AWS, and the Kubernetes project is one of the top-ranked projects on GitHub. In the upcoming lectures, we will take a quick look at Docker Swarm and Kubernetes. We will now get a quick introduction to Docker Swarm. Docker Swarm has a lot of concepts to cover and requires its own course, but we will try to take a quick look at some of the basic details so you can get a brief idea on what it is. With Docker Swarm, you could now combine multiple Docker machines together into a single cluster. Docker Swarm will take care of distributing your services or your application instances into separate hosts for high availability and for load balancing across different systems and hardware. To set up a Docker Swarm, you must first have hosts or multiple hosts with Docker installed on them. Then you must designate one host to be the manager or the master, or the Swarm manager as it is called, and others as slaves or workers. Once you're done with that, run the Docker Swarm init command on the Swarm manager, and that will initialize the Swarm manager. The output will also provide the command to be run on the workers. So copy the command and run it on the worker nodes to join the manager. After joining the Swarm, the workers are also referred to as nodes, and you're now ready to create services and deploy them on the Swarm cluster. So let's get into some more details. As you already know, to run an instance of my web server, I run the docker run command and specify the name of the image I wish to run. This creates a new container instance of my application and serves my web server. Now that we have learned how to create a Swarm cluster, how do I utilize my cluster to run multiple instances of my web server? Now, one way to do this would be to run the docker run command on each worker node. But that's not ideal, as I might have to log into each node and run this command, and there could be hundreds of nodes. I will have to set up load balancing myself, I will have to monitor the state of each instance myself, and if instances were to fail, I'll have to restart them myself. So it's going to be an impossible task. And that is where Docker Swarm Orchestration comes in. Docker Swarm Orchestrator does all of this for us. So far, we've only set up the Swarm cluster, but we haven't seen orchestration in action. The key component of Swarm orchestration is the Docker service. Docker services are one or more instances of a single application or service that runs across the nodes in the Swarm cluster. For example, in this case, I could create a Docker service to run multiple instances of my web server application across worker nodes in my Swarm cluster. For this, I run the Docker service create command on the manager node and specify my image name there, which is my web server in this case, and use the option replicas to specify the number of instances of my web server I would like to run across the cluster. Since I specified 3 replicas and I get 3 instances of my web server distributed across the different worker nodes. Remember, the Docker service command must be run on the manager node and not on the worker node. The Docker service create command is similar to the Docker run command in terms of the options passed, such as the -e environment variable, the -p for publishing ports, the network option to attach container to a network, etc. Well, That's a high-level introduction to Docker Swarm. There's a lot more to know, such as configuring multiple managers, overlay networks, etc. As I mentioned, it requires its own separate course. Well, that's it for now. In the next lecture, we will look at Kubernetes at a high level. We will now get a brief introduction to basic Kubernetes concepts. Again, Kubernetes requires its own course. Well, a few courses, at least 5, but we will try to get a brief introduction to it here. With Docker, you are able to run a single instance of an application using the Docker CLI by running the docker run command, which is great. Running an application has never been so easy before. With Kubernetes, using the Kubernetes CLI, known as kubectl, you can run 1,000 instances of the same application with a single command. Kubernetes can scale it up to 2,000 with another command. Kubernetes can be even configured to do this automatically so that instances and the infrastructure itself can scale up and down based on user load. Kubernetes can upgrade these 2,000 instances of the application in a rolling upgrade fashion, one at a time with a single command. If something goes wrong, it can help you roll back these images with a single command. Kubernetes can help you test new features of your application by only upgrading a percentage of these instances through A/B testing methods. The Kubernetes open architecture provides support for many different network and storage vendors. Any network or storage brand that you can think of has a plugin for Kubernetes. Kubernetes supports a variety of authentication and authorization mechanisms. All major cloud service providers have native support for Kubernetes. So what's the relation between Docker and Kubernetes? Well, Kubernetes uses Docker hosts to host applications in the form of Docker containers. While it need not be Docker all the time, Kubernetes supports alternatives to Docker as well, such as Rocket or CRI-O. Let us take a quick look at the Kubernetes architecture. A Kubernetes cluster consists of a set of nodes. Let us start with nodes. A node is a machine, physical or virtual, on which the Kubernetes software, a set of tools are installed. A node is a worker machine, and that is where containers will be launched by Kubernetes. But what if the node on which the application is running fails? Well, obviously our application goes down, so you need to have more than one nodes. A cluster is a set of nodes grouped together. This way, even if one node fails, you have your application still accessible from the other nodes. Now, we have a cluster, but who is responsible for managing this cluster? Where is the information about the members of the cluster stored? How are the nodes monitored? When a node fails, how do you move the workload of the failed node to another worker node? That's where the master comes in. The master is a node with the Kubernetes control plane components installed. The master watches over the nodes in the cluster and is responsible for the actual orchestration of containers on the worker nodes. When you install Kubernetes on a system, you're actually installing the following components: an API server, an etcd server, a kubelet service, a container runtime engine like Docker, and a bunch of controllers and a scheduler. The API server acts as the front end for Kubernetes. The users, management devices, command line interfaces all talk to the API server to interact with the Kubernetes cluster. Next is the etcd key value store. The etcd is a distributed reliable key value store used by Kubernetes to store all data used to manage the cluster. Think of it this way. When you have multiple nodes and multiple masters in your cluster, etcd stores all that information on all the nodes in the cluster in a distributed manner. etcd is responsible for implementing logs within the cluster to ensure there are no conflicts between the masters. The scheduler is responsible for distributing work or containers across multiple nodes. It looks for newly created containers and assigns them to nodes. The controllers are the brain behind orchestration. They're responsible for noticing and responding when nodes, containers, or endpoints goes down. The controllers makes decisions to bring up new containers in such cases. The container runtime is the underlying software that is used to run containers. In our case, it happens to be Docker. And finally, kubelet is the agent that runs on each node in the cluster. The agent is responsible for making sure that the containers are running on the nodes as expected. And finally, we also need to learn a little bit about one of the command line utilities known as the kube command line tool, or the kube control tool, or kubectl as it is also called. The kube control tool is the Kubernetes CLI, which is used to deploy and manage applications on a Kubernetes cluster to get cluster-related information, to get the status of the nodes in the cluster, and many other things. The kubecontrol run command is used to deploy an application on the cluster. The kubecontrol cluster info command is used to view information about the cluster, and the kubecontrol get nodes command is used to list all the nodes part of the cluster. So to run hundreds of instances of your application across hundreds of nodes, all I need is a single Kubernetes command like this. Well, that's all we have for now. A quick introduction to Kubernetes and its architecture. We currently have 3 courses on CodeCloud on Kubernetes that will take you from the absolute beginner to a certified expert. So have a look at it when you get a chance. So we're at the end of this beginner's course to Docker. I hope you had a great learning experience. If so, please leave a comment below. If you like my way of teaching, you will love my other courses hosted on my site at CodeCloud. We have courses for Docker Swarm, Kubernetes, advanced courses on Kubernetes certifications, as well as OpenShift. We have courses for automation tools like Ansible, Chef, and Puppet, and many more on the way. Visit CodeCloud at www.codecloud.com. Well, thank you so much for your time, and until next time, goodbye. Hello there. You're at the end of the course, so congratulations once again. A lot of my students reach out to me asking how to generate their course completion certificate. So I thought I'll quickly walk you through that process. When you select your course, you will see your progress in the top right corner. You should have completed 100% of the course to get your course completion certificate. Now, I would completely understand if you had to skip a few lectures that weren't as interesting to you, so don't worry, I'll show you how to mark them complete manually. Firstly, you need to identify the lectures that were not completed. Each topic in the course curriculum has a check mark next to it. Go through and find out which ones are missing a check mark and click on them to manually mark them complete. Once you do that for all, you should see the progress set to 100% at the top. And that's all you need to do. Refresh your page and give it a few minutes, and you should see the Get Certificate button. Click on the Leave a Rating button to rate or update your rating on the course. I always aim for a 5-star rated course, so write to me and let me know if you think otherwise. Now click on the Get Certificate button to get your course completion certificate. Click on the Download button to download it, or the Share button to share it. When you share on LinkedIn, don't forget to tag me in it. Well, thank you for joining me in this course once again, and I will see you in the next course.